Hello and welcome to Sleepy Science. I'm so glad you're here. What if I told you ice can turn hot and metallic, crystals can tick in time, atoms can swell into giants, magnets can refuse to freeze, and insulators can carry traffic only along their edges? That we bend light the wrong way, pool it like matter, chill chemistry to near nothing, float carbon on magnets, make liquids climb walls, and let sound or lasers hold droplets and cells mid-air, that chips freeze problem landscapes for tunneling. We read the almost unmeasurable root light that won't get lost, watch atoms move in femtoseconds, and compute with the twist of electrons. Real labs, real experiments, zero sci-fi. Before we dive in, where are you watching from, and what time is it there? Drop it in the comments. If this sparks your curiosity, please tap like and subscribe so you don't miss the rest of the journey. Superionic ice, a new phase that shouldn't exist. You think you know water because you've known it your whole life. Ice cubes rattling in a glass, rain on a window, steam fogging a mirror. But there is a version of water that belongs to the deep interiors of planets, and for most of human history, it was only a rumor whispered by equations. Superionic ice, a phase that looks like a solid, yet lets part of itself flow like a liquid. A paradox you can't pour, but that can carry electricity as if it were a wire hidden inside a crystal. To feel what that means, picture the heavy oxygen atoms freezing into a rigid lattice, like a scaffolding of stones, while the tiny hydrogen nuclei, the protons, slip their bonds and wander through the structure as freely as commuters moving through a subway. And because protons are charged, their motion turns this ice into a surprisingly conductive medium, more like the electrolytes inside a battery than the clear cubes in your freezer. What makes this real and not science fiction is the way we've learned to recreate the crushing pressures and scorching flashes of heat found thousands of kilometers under the clouds of Uranus and Neptune, where water does not politely choose liquid or solid, but becomes something in between. Researchers clamp a microscopic drop of water between the tips of two flawless diamonds, push until the pressure soars to millions of Earth atmospheres, then zap it with a laser pulse that lasts less than the blink of an eye. And while the sample is in that extreme state, they probe it with X-rays to read the positions of the atoms from the pattern of scattered light. The X-rays tell a consistent story. The oxygen network holds its crystalline order, while the hydrogens lose theirs, which is exactly what superionic means. Part of the material behaves like a solid, part like a liquid at the same time. And because the protons can move, the ice that forms under these conditions turns dark and opaque and starts to carry current, a shocking reversal of what you expect from ice. It matters far beyond the lab, because the odd magnetic fields of Uranus and Neptune, tilted, offset, patchy in ways that don't match a simple textbook dynamo, may be born in layers where water, ammonia, and methane are squeezed into a superionic regime. So the electrical currents that sustain those fields run not through a molten metallic core like Earth's, but through a shell of proton-conducting hot ice, and that shell, being thinner and more complex than a vast metal ocean, naturally creates a magnetic geometry that looks broken unless you know what kind of matter is doing the work. Even if you never set foot near a diamond anvil cell, you can recognize the deeper lesson hiding here. The phase diagram of water, the map that says which form exists at which temperature and pressure, is not a triangle of solid, liquid, and gas, but a sprawling atlas with neighborhood after neighborhood of exotic crystal structures, and superionic ice is one of its strangest districts. A reminder that the rules you learn at room conditions are local customs, not universal laws. Part of the beauty is how the effect springs from simple ingredients you already understand. Oxygen is heavy and tends to sit still once locked into a lattice. Hydrogen is light and mobile. Pressure squeezes molecules so close that hydrogen bonds rearrange, and heat gives protons just enough energy to hop from site to site. Together, those small facts create a state that once sounded impossible. In the lab, the evidence is cross-checked with different techniques. Optical measurements that show the ice turning dark as its electronic gap narrows. Conductivity readings that spike when protons start roaming. diffraction patterns that reveal the oxygen skeleton holding steady. And because the state only exists while the pressure and temperature are just right, scientists repeat the dance again and again, pressing, heating, probing, letting it relax, then pressing again until the signatures line up and the picture holds. Beyond the headlines, practical implications begin to surface. The way protons zip through a rigid framework hints at design principles for future materials that move ions efficiently without melting. A dream for solid-state batteries or fuel cell membranes, if we can find chemistries that mimic the same trick at less punishing conditions. Even the name Superionic tells you what to remember. This is not a metal with electrons rushing freely, and it's not ordinary ice with locked-in molecules. It's a hybrid where ions themselves do the moving, a state that blurs your neat categories. And if you're tempted to shrug because you don't live inside an ice giant, consider how many certainties in your life depend on the gentle corner of the universe you occupy. Change the pressure a little, change the temperature a little, and what looked like a rule reveals itself as a preference. Superionic ice is nature admitting that matter has more options than your day-to-day senses can catch, and it invites you to think more flexibly about what things are. Because sometimes the truest description needs two words that sound as if they don't belong together. Super and ionic, solid and liquid, fixed and flowing. That is the quiet wonder of this phase that shouldn't exist, and yet does. And as you let the idea settle, you may feel a soft echo in yourself. Parts of you are anchored, reliable, lattice-like. Parts of you are mobile, learning, ready to move through pathways you couldn't see before. And when those two selves cooperate under pressure, you become something you haven't been yet. More capable, more conductive to what matters. Proof that in extreme conditions, new forms of order aren't just possible, they are waiting. Time crystals, structures that repeat in time. Imagine a material that refuses to dance on your beat. You poke it at a steady rhythm, but it answers on every second or third step, and keeps doing that with uncanny reliability even if your timing wobbles. That stubborn timing is the essence of a time crystal, a state of matter where order appears not as a repeating pattern in space like a snowflake, but as a repeating pattern in time. And to understand why that's surprising, you need one simple idea about nature's habits. If you leave most systems alone, they drift toward featureless calm. Vibrations fade, motion blurs into heat, and the details wash out. Yet a time crystal flips this script by living out of equilibrium, under a gentle periodic nudge that would normally smear things further. And somehow it stabilizes a new kind of order that ticks predictably at a slower pace than the nudge itself. In ordinary language, you tap once every t seconds, and the system replies every 2t or 3t, a subharmonic response that is locked in, not by an external metronome, but by the system's own internal interactions. And that locking is the key, because it means the timing persists, even when your taps are imperfect. Almost like a chorus that naturally falls into a slower refrain, no matter how the conductor flicks the baton. This does not break any laws of physics or build a perpetual motion machine. Time crystals do not run forever on their own, and they do not deliver free energy, because the periodic drive is essential, and the system does no net work on the outside world. It simply organizes its motion into a protected rhythm instead of heating up into disorder, as many driven systems do. What protects that rhythm are the microscopic conversations among the particles, spins, atoms, or quasiparticles, whose interactions can prevent energy from spreading freely. A phenomenon that, depending on the platform, goes by names like many-body localization or pre-thermal stability. But all you need to hold is that the energy from the drive gets trapped locally or sloshes very slowly, so the system avoids the fate of becoming a hot, featureless soup and can sustain a clean repeating beat. In the lab, this has been seen in different ways. Chains of trapped ions, where each ion's internal state acts like a tiny compass needle. You can flip with laser pulses, arrays of spin defects in diamond that behave like a dense jungle of little magnets, and clouds of ultra-cold atoms where light provides both the lattice and the timed kicks. And across these platforms, the telltale signature appears when you look stroboscopically, checking the system only at the moments you kick it, and find that a measurable quantity, like the average orientation of those tiny magnets, flips sign. Every other kick or cycles through a stable pattern. Every few kicks, and crucially, it keeps that rhythm even if you vary the strength or timing of your pulses a bit. This robustness is the difference between a genuine time crystal and a mere metronome effect. A fragile system would track your drive exactly and fall apart with small errors, whereas a time crystal shows a rigid subharmonic peak in its measured spectrum that refuses to budge until you push it past a threshold. To reach that regime, experimentalists tune a balance. Too strong a drive and the system heats up and loses structure. Too weak and there's nothing to organize. But in the middle, there is a window where interactions corral the energy and the repeating pattern sets in. And the observation itself is careful, because measuring quantum systems can easily scramble them. So protocols look for global, repeating features you can read gently without erasing the very order you want to see. The theoretical backdrop adds another layer of wonder. In thermal equilibrium, the idea of a constantly repeating motion is ruled out for stable phases, which is why early proposals for equilibrium time crystals ran into strong no-go arguments. But once you allow a periodic drive, a world that ticks because you tap it, new categories open up. Floquet phases, where time translation symmetry is not continuous but discrete. And breaking that discrete symmetry becomes as legitimate, a form of order as the spatial symmetry breaking that gives you standard crystals. What could this be good for beyond satisfying curiosity? The most immediate promise is in quantum technologies, because the same rigidity that locks a time crystal's beat could help store or process quantum information more reliably, offering a kind of built-in error protection against the small timing drifts and environmental jitters that plague delicate devices. And researchers are already exploring whether domains of a time crystal can act like robust memory cells, or whether the subharmonic response can serve as a noise-resistant clock signal for controlling larger systems. There's also a sensing angle. If your material insists on oscillating at half the drive frequency, any external disturbance that tries to pull it off that ratio becomes glaringly obvious in the readout, which could translate to sensitive detection of tiny fields, strains, or temperature shifts embedded in the timing. Even without a gadget on the horizon, the concept itself expands the map of matter. Phases are no longer just arrangements of atoms in space or alignments of spins in a static field. They can be patterns of motion protected by interactions and repetition, and that means what counts as stable is broader than stillness. It can be a dance that never loses step. To keep the picture honest, it's worth noting limits. Time crystals are not magic. They require careful conditions. They can melt if disorder is too weak or the drive is too strong, and they are observed over long but finite times in realistic systems. Yet those practical boundaries don't blunt the conceptual shift. They sharpen it by showing the precise ingredients needed for time to become a stage for order. Perhaps the most human way to feel this is to think about routines in your life that survive small disturbances. Sleep cycles that slowly relock after travel. A breath pattern that calms you no matter how chaotic the day has been. A weekly ritual that keeps its meaning even when the hour changes. These are not scientific time crystals, but they rhyme with the idea that stability can live in repetition rather than rest, and that meaning can appear when motion returns to itself. So when you hear the phrase, structures that repeat in time, don't imagine a clockwork gimmick or a loophole in the laws of thermodynamics. Imagine a world where interaction and rhythm carve a groove into the future, where a gentle nudge and the right crowd of particles produce a tempo that belongs to the system, not the pusher, and consider what that implies for how we think about control, memory, and order. Sometimes the most resilient things are not the ones that sit still, but the ones that keep coming back, beat after beat, no matter how the world tries to rush them. Rydberg atoms, giant atoms with exaggerated rules. Start with a picture that breaks your intuition. An atom swollen until it's big enough to cast a tiny shadow under a microscope. not because you added more protons or neutrons, but because you coaxed a single electron to wander so far from home that the atom's footprint balloons to sizes 1,000 times larger than usual. This is a Rydberg atom, the gentle monster of atomic physics, where familiar rules still apply, but their effects are turned up so loudly that quiet interactions become thunder, and the ordinary becomes a tool you can sculpt, one photon at a time, into logic, simulators, and sensors that nibble at the edges of what's possible. The recipe is conceptually simple. You take a neutral atom you already know how to handle, rubidium, cesium, strontium, cool it until its motion slows, trap it in a tiny focus of light so it holds still, and then deliver a carefully chosen burst from a laser that lifts its outermost electron to a very high energy level. At that altitude, the electron's average distance from the nucleus swells dramatically, the atom's polarizability skyrockets, and even faint electric fields tug on it as if the electron were a kite on a mile-long string. That exaggerated sensitivity is not a bug, it is the feature. Bring two of these giants within a few micrometers, and they feel each other's presence so strongly that the excitation of one shifts the energy levels of the other, a self-imposed rule known as the Rydberg blockade that says, in essence, if I'm excited, you can't be, at least not in the same way. With that single interaction, you get a switch. The state of one atom controls the fate of its neighbor, which is exactly the primitive you need for quantum logic gates. Now imagine hundreds of neutral atoms held in place by a grid of optical tweezers, pinpricks of light arranged like seats in a theater, and you begin to see why this field has sprinted forward. You can draw your own lattices, move atoms around, with light like chess pieces, decide who talks to whom, and watch as patterns of magnetism, glassy dynamics, or exotic phases blossom from the rules you programmed. Because the giants interact at a distance, you can link atoms without wire or waveguide, and because they start neutral, they are wonderfully quiet when you want them to rest. But the story of giant atoms is richer than computing alone. Those same swollen orbitals let you craft matter-light hybrids and create optics that behave in ways your high school intuition would never predict. By letting a weak probe beam pass through a vapor where some atoms are tickled into Rydberg states, you can make single photons nudge each other, turning a medium that was once transparent into a stage where light exhibits a kind of traffic etiquette. One photon persuading the next to slow down or take a different path. Push a little further, and the Rydberg atom becomes a near-perfect antenna for radio and microwave fields. Because its energy levels are spaced like rungs on a wildly tall ladder, it responds vividly to the faintest whispers in those bands, enabling sensors that read electric fields with a precision that would be unthinkable with ordinary materials at room temperature. There are even bonds here that barely look like chemistry at all. The diffuse electron cloud of a Rydberg atom can enfold a ground-state neighbor and form a molecule held together not by the usual tug-of-war over shared electrons, but by the way the wandering electron scatters from the intruder, painting knotty, long-range shapes that stretch far beyond the scale of familiar molecules. It's as if an electron's fog briefly decides to hug a passerby. Of course, everything powerful in the quantum world has edges you must respect. These atoms are fragile. Blackbody radiation from the room can jostle the electron off its perch, stray charges on nearby surfaces bend the energy levels, and the very property that makes them sensitive also makes them fussy. So experimenters shield, compensate, and choreograph with care, shaping pulses that excite and de-excite in microseconds so the atom does its work before the environment steals the show. But inside those constraints lies controllability that feels almost animated. You can tune the strength and range of interactions by choosing which excited level to target. You can switch between different angular momenta to change the texture of how atoms talk. You can dress ground-state atoms with a hint of Rydberg character to borrow strong forces without fully paying the price in fragility. And you can watch entire quantum neighborhoods evolve in real time, detecting outcomes by making the atoms fluoresce, or by gently ejecting the high-lying electron and counting the result. For you, the non-technical takeaway is this: by giving one electron more room, you amplify the atom's ability to sense and to influence, which turns a cloud of identical, quiet particles into a programmable material, an addressable canvas for exploring magnetism, building logic, and measuring fields so weak they would otherwise pass unnoticed. And there's a human echo running through it. Sometimes the most transformative change comes not from adding complexity, but from granting something space to roam, to become responsive, to connect. Rydberg atoms are a physics version of that lesson, proof that expansion can create capability, that distance can breed dialogue, and that rules you thought were mild can, when stretched, write entirely new stories. As this field matures, arrays grow larger, gate fidelities rise, and clever ways to suppress noise keep arriving, but the deeper significance is already clear. We have learned to engineer conversations at the single atom level, and to let those conversations build structures of thought and function, an architecture of the microscopic that you can change with a sentence of light. Hold that for a moment. A giant atom made with a gentle push, talking to another giant atom across an invisible gap, both waiting for your next instruction. The science is real, the possibilities are open, and the quiet thrill is knowing that matter, when given room and rhythm, can be persuaded to compute, to simulate, and to sense in ways that feel less like machinery and more like choreography. Exaggerated rules, yes, but rules that you can learn to conduct. Quantum spin liquids, magnetism that never freezes. Picture a magnet that refuses to make up its mind. You cool it further and further, past the point where iron would line up into rigid domains, past the temperature where ordinary spins would lock into a tidy pattern, and yet the moments keep fluctuating, quietly, coherently, forever, like a murmuration that never lands. And this is the strange promise of a quantum spin liquid, a phase where magnetism refuses to freeze even at the lowest reachable temperatures, not because of disorder or thermal jitter, but because quantum mechanics keeps the spins in motion. To see why that matters, you need only one idea: frustration. Spins trying to satisfy conflicting preferences on a lattice whose geometry makes it impossible for everyone to be happy at once. The triangular and Kagame arrangements are classic examples, where each spin wants to anti-align with its neighbors and can't. So instead of picking a single arrangement and sitting still, the system explores many nearly equivalent patterns at once, superposing them into a fluid of entanglement, rather than a crystal of order. And this is where the liquid metaphor earns its name. The earliest intuitive picture came from the resonating valence bond idea. Imagine the spins pairing up into tiny singlets, like handshakes between neighbors, but with those handshakes constantly rearranging around the lattice, so no bond is permanent and no pattern repeats. A living, breathing network of partnerships that yields no static Bragg peaks when you look with neutrons, only a broad continuum that signals fractional excitations instead of tidy spin waves. Those fractional excitations, often called spin-ons, carry a bite of the original spin without dragging along the whole moment. So in a sense, the magnet's fundamental disturbance splits apart, a hallmark of deconfinement that turns the background into more than a backdrop. It becomes an emergent world with its own gauge fields that guide the motion of these pieces. And depending on the details, you may get a Z2 spin liquid with anyone-like statistics, or a U1 spin liquid whose low energy excitations behave like gentle, photon-like ripples of an internal field. Not light in space, but light in the language of the spins themselves. If that sounds abstract, experiments give it weight. In candidate materials like the Kagome mineral Herbert Smithite, neutrons scattering looks for sharp spikes that would mark a frozen pattern and instead sees a smear, a broad energy-spanning signature that screams no simple order, while nuclear magnetic resonance and muon spin techniques listen for the telltale slowing down that precedes a magnetic transition and hear persistent motion down to the coldest settings and heat. Capacity measurements show unusual low-temperature tails, sometimes close to linear, that hint at gapless excitations moving through the spin sea. The family of candidates is growing and diverse. organic salts on triangular lattices, layered ruthenium halides with bond-directional interactions inspired by Kitaev's exactly solvable model, ytterbium compounds with delicate exchange pathways, even quantum spin ice pyroclores, where classical ice rules meet quantum tunneling and give rise to emergent magnetic monopoles and a faint, internal light mode. Each material teaches a slightly different dialect of the same idea. When geometry and quantum motion conspire, the spins keep their options open. The stakes are not just academic, because a liquid of entanglement can be robust against local noise in a way that static order is not, and this robustness is the seed of dreamlike technologies, fault-tolerant memories encoded in the global pattern rather than in any single atom, braids of anionic quasiparticles that store information in how paths wind rather than where bits sit. But it's honest to say that such devices are future tense. The cleanest models live in theory, and carefully tuned experiments are still wrestling with impurities, finite temperatures, and competing phases that sometimes masquerade as liquids. Even so, concrete signatures keep accumulating. No static field at the nuclear sites, a dynamic susceptibility that refuses to collapse, thermal transport that hints at neutral carriers, and in a few controversial cases, unusual thermal Hall responses, under fields that may point to exotic excitations roaming the lattice, tantalizing, debated, and motivating better crystals and sharper probes. What makes all of this worth your attention is not only the physics, though it is beautiful, but the redefinition of what it means for a system to be ordered. Because here, the order is not in a repeating snapshot, but in the pattern of motion itself, in the web of quantum correlations that never picks a single picture, yet remains stable as a whole. Like the identity of a song that survives changes in key and tempo as long as the relationships among notes hold, to feel the human echo. Think of moments when you've tried to arrange every piece of your life into a perfect, static alignment and discovered that the attempt squeezes out the very vitality you were chasing, and then recall times when you allowed a bit of frustration to remain, conflicting goals, competing pulls, and instead of choosing once and freezing, you kept moving, letting small bonds form and reform while the whole stayed coherent, resilient, alive. A quantum spin liquid is the physical proof that such a stance can be stable, that not deciding on a single pattern can be a decision, enforced not by disorder or confusion, but by deep rules that prefer motion to stasis. And as you let that sink in, you can appreciate the quiet power of the idea. Matter can hold together without picking one arrangement. Memory can live in relationships rather than positions, and complexity can be gentle if the background is entangled enough. So when you hear magnetism that never freezes, don't imagine chaos, imagine grace. Spins in a patient conversation that never ends, a lattice that chooses to keep learning, and a phase of matter that shows you how stability can be a dance with no final pose. Topological insulators, edge highways that ignore disorder. What if the easiest path for electricity wasn't through the middle of a material, but around its rim? Like a city where traffic flows flawlessly along the coastline while the downtown grid is closed to cars. And what if that shoreline highway kept moving even when you threw debris onto it? That is the counterintuitive promise of topological insulators, solids whose interior behaves like an electrical desert, while their boundaries host special lanes of current that shrug off ordinary potholes and detours. And to see why this is more than a clever metaphor, you can start with a simple contrast. In a normal insulator, electrons are trapped because their allowed energies sit in separate bands with a gap in between. But in a topological insulator, the overall pattern of those bands is twisted in a way that cannot be untwisted without breaking the material's identity. So the surface or edge is forced to carry states that bridge the gap and let electrons move. This twist is not about a literal spiral inside the crystal. It's a global property, like the difference between a coffee mug and a donut, which share a hole and can be reshaped into one another without cutting, whereas a bowl cannot. So, long as you don't tear the electronic structure by closing the gap or breaking the protecting symmetry, the system must host conducting boundaries, and that obligation is what makes the edges special rather than accidental. On a two-dimensional sample, the boundary reduces to narrow channels that hug the perimeter. And on a three-dimensional crystal, the boundary is a metallic skin. And in both cases, there is a striking rule called spin momentum locking. The direction an electron moves is tied to the orientation of its tiny magnetic moment, so turning a particle around would require flipping that moment as well, which ordinary non-magnetic bumps can't do efficiently, meaning backscattering, the process that usually kills current, is strongly suppressed. You can picture two helical lanes running opposite ways around the edge, one lane for spin pointing one way, the other for the opposite spin. And because an impurity that lacks magnetism can't easily swap you between lanes, traffic glides through, the clutter with a grace you don't see in typical conductors. This is not a fairy tale. In thin quantum wells built from carefully stacked semiconductors, researchers saw that edge conductance stayed close to a fixed value independent of the channel's length, a hallmark of robust one-dimensional transport. And in bulk crystals like bismuth selenide and bismuth telluride, angle-resolved photoemission, basically a microscope for electron motion, captured the surface band structure as a clean, cone-shaped crossing right in the middle of the energy gap. The fingerprint of those protected linear dispersion states. Scanning probes went further by sprinkling disorder and looking for the standing wave patterns that backscatter usually creates, only to find certain wave vectors missing, as if the electrons refused to echo backward unless magnetism was involved, and transport experiments echoed the same message. Non-magnetic roughness barely dented the edge current, while magnetic dopants, or an applied magnetic field, opened a gap in the surface spectrum and tamed the flow, showing the protection isn't invincibility but a shield with clear conditions. That distinction matters because ignore disorder does not mean ignore everything. Temperature can still excite carriers into the bulk. Defects can unintentionally dope the interior and let current leak through, and magnetic impurities or fields can break the time reversal symmetry that keeps the lanes separated. So much of the practical work is about making cleaner crystals, pushing the Fermi level into the true gap, and patterning devices that emphasize edge paths while suppressing unwanted bulk routes. When those conditions are met, the edge highways unlock possibilities that were science fiction a decade ago. Low dissipation interconnects where information rides around corners without bouncing back. Spin-based electronics in which a voltage controls flows of angular momentum directly. And in the most daring proposals, platforms where pairing the surface with a superconductor could turn those helical lanes into stages for exotic quasiparticles that store information non-locally and resist the usual kinds of noise. Even without jumping to that frontier, engineers are already experimenting with magnetic overlays that gap the surface states in a controlled way and create one-way boundary channels, the quantum anomalous Hall effect, so precise they can carry quantized amounts of current at zero external field, a route toward resistance standards and ultra-stable switches if the operating temperatures can be pushed higher. You don't need the jargon to grasp the heart of the idea. Most materials care about local details. If you dent the road, drivers slow. But a topological insulator cares about the global pattern. So long as that pattern stays intact, the boundary lanes reappear and recommit to their role. And that kind of robustness is rare in nature. To make the picture concrete, imagine designing an electronic map where the center is intentionally empty, then choosing a rule that says whoever walks clockwise must keep their spin pointing east, and whoever walks counterclockwise must keep it pointing west. Now litter the walkway with non-magnetic pebbles and watch. People can jostle, they can be delayed, but they almost never reverse. Because reversing violates the rule unless you add a magnetic signpost that lets them flip, and that is why these edge channels are so hard to localize. The scientific origin story is also a lesson in creativity. Starting from the quantum Hall effect, where magnetic fields carve one-way streets along the edges, theorists asked if spin-orbit coupling inside certain lattices could mimic that trick, without external fields, and with two counter-propagating lanes rather than one. And experiments with mercury-based wells answered yes, opening a flood of materials, from layered bismuth compounds to designer monolayers on specific substrates where heavy atoms and geometry collaborate to invert bands and force the boundary to conduct. there is honesty to keep in view. Many famous samples still require cryogenic temperatures for their best behavior, and getting a truly insulating bulk alongside a perfectly clean surface is a manufacturing challenge that teams are still perfecting. But year by year, the recipe is improving. Better growth, smarter gating, more precise control of impurities, and as these practical kinks are ironed out, the deeper message grows clearer. You can build stability not by polishing every atom into obedience, but by choosing a global structure that forgives small mistakes. That insight isn't only about electrons, it's a design philosophy for complex systems in general. Make the important features depend on a pattern that is hard to change by accident, and your creation will keep working in messy, real conditions. So when you hear edge highways that ignore disorder, don't imagine magic. Imagine a clever use of symmetry and geometry to route motion where it is safest. Imagine a boundary that stays faithful because the whole insists on it. And imagine what it means for your own projects if you can bake that kind of robustness into their foundations. Less energy wasted fighting the bumps, more purpose carried smoothly to the edge, and a reminder that sometimes the most reliable path forward is not straight through the center, but along a carefully protected rim. Metamaterials with negative index, bending light the wrong way. Pretend you're watching a beam of light hit a glass block on a lab bench and bend the familiar way toward the denser material, like rain slanting under wind. Now flip the scene so the beam bends the wrong way, refracting on the opposite side of the normal as if the glass were playing a prank on geometry, and you've met the unsettling idea behind negative index metamaterials, engineered media, whose internal structure, not their chemical recipe, tells waves to do things nature's usual catalog rarely allows. The core trick is simple to say and hard to build. Instead of relying on atoms to set the optical response, you pattern tiny repeating elements, little loops, wires, split rings, fishnet lattices, each smaller than the wavelength you care about, so that to the light, the pattern looks like a uniform material with properties you dial in by design. And if you arrange those meta-atoms so that both the electric and magnetic pieces of the wave are driven in an unusual phase relationship, the composite responds as though its refractive index is negative, which means the direction of energy flow and the direction of the wave's crests point opposite ways. What falls out is a set of counterintuitive but very real behaviors. Apply Snell's law, and the refracted beam appears on the other side of the normal. Make a prism and the image forms where your everyday intuition says it shouldn't. Watch the phase fronts march backwards while the energy still marches forward, and, even stranger, predict effects like a reversed Doppler shift and a backward version of Cherenkov radiation, the optical equivalent of a boat wake that leans upstream. The first clear demonstrations lived at microwave frequencies, where making sub-wavelength structures is friendlier. Metallic, split-ring resonators act like tiny magnetic springs, paired with wires that play the electric role, and together, they produce the composite response needed to push the index below zero. But the engineering urge kept pushing up in frequency, through terahertz and into the near-infrared and parts of the visible, using clever stacks of metal and dielectric fishnets, while a newer branch, metasurfaces, flattened the idea into a single patterned sheet that sculpts phase on demand, and can deflect, focus, or twist light with ultra-thin optics. This is the piece that speaks to you directly. We can now design lenses that look like simple flat plates, yet focus as if they were bulky glass. We can steer beams electronically without moving parts. We can squeeze antennas so they do more with less space, and we can craft absorbers that drink a whole band of wavelengths with almost no reflection. Ideas that seed better cameras, lighter headsets, compact satellites, and instruments that once demanded heavy, fragile stacks of glass. But the most famous promise is the super lens, a slab that could, in principle, image details smaller than the usual diffraction limit by amplifying the near fields. Those delicate, non-propagating ripples that hug an object and normally die off before they reach your detector, so that sub-wavelength features reappear on the other side. which ignited decades of work on sub-diffraction imaging with metamaterials and with cousins called hyperbolic media that support unusually large wave vectors. Here, honesty helps. These breakthroughs are real and exciting, but they arrive with conditions. Most negative index designs are strongly dispersive, meaning they work over narrow bandwidths, and metals at optical frequencies are lossy, which eats the very signal you want to preserve. So a super lens that dazzles at a single color may stumble when asked to handle a rainbow. And a cloak that diverts microwaves around a bump on a plane wing won't make you invisible in daylight. That famous invisibility headline is grounded in a rigorous framework called transformation optics, where you map desired pathways for light as if you were drawing lanes on a curved space, and then build a material whose spatially varying pattern forces light to follow those lanes, and it does work. In narrow bands, in 2 dimensions, at scales where you can fabricate the pattern. But translating that into a full spectrum, walk-through cloak for human vision is far beyond current loss and bandwidth limits. Still, the practical wins are stacking up. Flat lenses that replace stacks of glass in compact cameras, beam shapers that let LiDAR scan without spinning mirrors, antennas whose footprint shrinks while their performance improves, microwave components that guide signals around bends with minimal reflection, and laboratory microscopes that take peaks below the usual resolution line by tapping near-field tricks on specialized samples. If you worry that bending light the wrong way breaks causality, it doesn't. Energy still flows forward, signals still respect the speed limit, and what looks like backward motion is the phase of the wave, not the information you send on it, so there's no time machine hiding in a patterned film. What's happening is that the material's collective response makes the wave's bookkeeping run in reverse, while the actual transport carries on sensibly. Beyond optics, the same blueprint has migrated to sound and heat. Acoustic metamaterials bend and focus sound with negative effective parameters, enabling ultra-compact mufflers, noise shields, and even acoustic lenses that can sharpen medical ultrasound, while thermal metamaterials guide heat around sensitive regions like a temporary cloak for temperature. And electromagnetic cousins at radio frequencies have already improved antennas on aircraft and phones by taming interference and shaping radiation patterns with light, robust lattices. Perhaps the deepest lesson to carry with you is that metamaterials are a vote for design over discovery. Instead of asking nature for a material that happens to have the combination you dream of, you teach a simple substance to behave that way. By carving it into the right geometry, and because geometry can be scaled, the same principles reappear across frequencies with the proper choice of pattern and size, letting microwave engineers, optical physicists, and even acousticians speak a shared language. Still, your skepticism is healthy. Losses remain a hurdle. Fabrication at visible wavelengths is expensive and painstaking, and many eye-catching demonstrations live in controlled conditions. But the direction of travel is clear as techniques. Improve. Better dielectrics that mimic magnetic responses without metal losses. Clever, all-dielectric metasurfaces that use high-index nanoposts to delay light without ohmic heating. Tunable platforms that swap static patterns for reconfigurable ones using phase change films or tiny actuators. And hybrid systems that marry metamaterials with chips, so beam steering and focusing become software tasks. So when you hear negative index, don't translate it as hype. Translate it as a new grammar for waves. One that writes sentences. Light isn't used to saying, where a slab can focus, a surface can steer, and a thin patterned film can replace a library of glass. And let that expand how you think about design in your own life. Sometimes you get farther by patterning the environment than by pushing harder through it. Sometimes the shortest path is a cleverly arranged detour, and sometimes the rule you thought was universal, the beam must bend this way, turns out to be a habit, one that yields as soon as you change the structure of the world it moves through. Photonic, Bose, Einstein, Condensates. When light acts like matter. You've always been told that light is the restless traveler of the universe, massless, untouchable, always moving. So the notion that light can settle down and behave like A pooled substance sounds like a fairy tale until you walk into a lab where mirrors coax photons into doing exactly that, forming a photonic Bose-Einstein condensate, a state where countless particles of light fall into the same mode and act in unison as if they were one, not by lacing in the usual sense, but by actually thermalizing, sharing energy the way a gas does until a threshold is crossed and the lowest state floods with occupancy. To get there, you start with a tiny optical cavity made from two highly reflective mirrors placed so close together that only specific colors and angles of light can survive inside, and you fill the space between with a dye solution whose molecules absorb and re-emit photons over and over, like a crowd passing notes across a room until everyone agrees on the same temperature. And as those countless exchanges take place, the photons give up memory of how they were made and adopt a well-defined energy distribution at room conditions, something free light never does, because it doesn't bump into much and its number isn't fixed. The cavity quietly changes the rules by giving light an effective restlessness that looks like mass, and by letting you adjust how many photons live inside, so instead of diluting away when you try to cool them, as ordinary photons do in the open, the population can be held steady with a gentle pump, while the repeated absorption and emission with the dye gas shepherds the spectrum toward equilibrium. And once the number per allowed phase space volume climbs high enough, the photons pile into the lowest available mode, the way cold atoms pile into the ground state of a trap, not one by one, but as a collective fall that you can see as a sudden bright spot at the cavity center. At first glance, you might mistake that spot for a laser dot, and the temptation is fair. Both are coherent, both are bright. But the engine under the hood is different. A laser is a driven, non-thermal process that relies on population inversion and stimulates copies of a specific mode, whereas the photonic condensate arises from something closer to everyday statistical mechanics, a thermalized distribution whose numbers swell until condensation is the most probable outcome. And you can tell the difference by how the light's spectrum looks, how the population behaves near threshold, and how the system responds when you tweak temperature or the cavity's geometry rather than just adding gain. The mirrors do more than confine. They shape the landscape the photons feel, because the spacing and curvature define which modes cost more energy, and a pair of gently curved mirrors creates a bowl-like potential in 2 dimensions where the lowest mode is at the center, and higher modes are rings around it. So as the pump increases and thermalization keeps pace, the cloud of light shrinks and brightens into a clear, minimal state whose size and frequency you can predict from the cavity's design, an optical version of watching a mist settle into a pond. While this might sound exotic, the beauty is that many such experiments run near room temperature. No liquid helium baths, no ultra-high vacuum beyond what the cavity needs, because the mass and temperature the photons acquire are set by the cavity spacing and the dye, rather than by cosmic conditions, which turns the setup into a tabletop playground for studying big ideas like phase transitions, fluctuations, and collective coherence with equipment that fits on an optical table. There are close cousins worth knowing. Polariton condensates, for instance, where light mixes strongly with excitations in a semiconductor to create hybrid particles that also condense and even show hints of frictionless flow. But the dye microcavity condensate is different in that it keeps the photons more light-like, using repeated absorption emission to thermalize without binding the photons permanently to matter, a distinction that changes details like lifetimes, interactions, and how you push the system around. Speaking of interactions, photons normally ignore each other, so how does a condensate avoid spreading out like an indifferent fog? Part of the answer is that the cavity restricts the number of available states, and the dye supplies an environment that nudges everyone into line, and subtle effective interactions can arise from how the dye saturates, or how the refractive index shifts with intensity, which means you can watch behaviors beyond simple piling up, such as vortices in the phase pattern or gentle repulsion that shapes the cloud, though these effects are delicate and require careful tuning to reveal. On the measurement side, the signatures are satisfying to chase. Spatial images show the sudden central brightening and narrowing of the mode at threshold. spectra collapse toward the lowest frequency allowed by the cavity with a thermal tail. Above it, correlation measurements track how the light's fluctuations change as the system goes from a soup of independent photons to a single coherent field. And by adjusting temperature, pump power, or mirror spacing, you can move the condensate around like a droplet in a dish. It's tempting to leap straight to science fiction, perfect rooms of glowing quantum fluid, but responsible excitement notes the limits. Dye molecules slowly degrade under intense pumping. Losses and reabsorption shape how uniform the temperature really is. The coherence length and time are finite, and distinguishing the condensate cleanly from laser action requires care because both produce bright, narrow light. Even so, the practical promise is real. Novel light sources that work without traditional inversion, sensitive platforms for probing thermodynamics in an optical language, adaptable simulators where you sketch a potential with mirrors and watch a quantum fluid of light settle into it, and perhaps future devices that combine the best of lasers and condensates, tunability from design, coherence from collectivity, and room temperature operation from clever thermal coupling. The deeper lesson for you is philosophical as much as technical. When you constrain light just enough and give it a way to share energy like a gas, it learns to rest in a shared state, reminding you that many behaviors we file under impossible are merely unnatural under everyday conditions, and that by shaping the environment, mirrors, spacing, a medium that gives and takes, you can persuade even the most flighty things to cooperate. In that sense, a photonic condensate is a quiet parable about attention and context. What you hold, reflects, and allow determines how scattered energy becomes a single thought, how a rush of photons turns into a calm, unified glow, and how something known for speed discovers, for a moment, the surprising power of stillness. Quark-gluon plasma, recreating the first microseconds. Imagine turning matter up so hot and squeezing it so hard that the familiar building blocks of protons and neutrons, quarks bound by gluons, let go of each other and roam freely for an instant, as if you had briefly rewound the universe to its first microseconds and dipped a thermometer into the newborn fire. That is the quark-gluon plasma, not a theoretical fantasy, but a state we now make on Earth by smashing heavy atomic nuclei together at nearly light speed, creating droplets of early cosmos conditions that live for a few trillionths of a trillionth of a second and then cool into ordinary particles we can count. The recipe is brutal and precise. Accelerate gold or lead ions until each nucleon carries enormous energy. Collide two nuclei so their overlapping almond of matter is instantly heated to temperatures of several trillion degrees, hotter than the center of any star, and watch as the quarks and gluons inside lose their confinement and form a liquid so dense and lively that it flows almost without internal friction. Detectors with names you learn to trust, STAR and Phoenix in New York, ALICE, ATLAS, and CMS at CERN, don't see the plasma directly because it vanishes as it expands and cools, but they read its fingerprints in the particles and patterns that stream to their sensors. Thousands of hadrons fanning out with subtle pushes and squeezes that reveal how the droplet once moved. High-energy jets from the initial collision, emerging lopsided or dimmed because they plowed through dense matter and bled energy. Bound states of heavy quarks, like bottomonium weakening, in a neat order that tells you how strongly the medium screens. Color forces, and an unexpected collective rhythm, elliptic flow and higher harmonics that hydrodynamics can describe only if the fluid's viscosity is astonishingly small. This is the point that surprised even many experts. The plasma behaves not like a thin gas of free partons, but like a strongly coupled liquid, a near-perfect fluid that converts the initial geometric asymmetry into coordinated motion with remarkable efficiency. And the fact that simple fluid equations work so early and so well implies the droplet thermalizes with stunning speed. What anchors the first microseconds claim is a clean reference from theory. Lattice calculations of quantum chromodynamics predict that, at vanishing net baryon density, quarks should deconfine around a temperature equivalent to about 150 million electron volts, and experiments infer temperatures safely above that threshold. Through the spectra of emitted photons and the composition of the resulting hadrons, which freeze out chemically close to the values those calculations anticipate. The story deepens as you vary the collision energy. At the very highest energies, the matter hovers near zero net baryon density, like the early universe after its first fractions of a second, while lower energy programs scan a broader phase diagram, where a transition might sharpen or a critical point could hide, so teams systematically step the beam energy down and look for non-monotonic fluctuations that would betray a change in the underlying order. Meanwhile, the small system surprise keeps theorists honest. Collisions of protons with heavy ions, once expected to be too tiny for fluid behavior, sometimes display collective patterns that look like miniaturized flow, raising questions about how small a droplet can be and still act like a liquid, and what initial correlations might masquerade as hydrodynamics. Yet across these debates, several anchors hold. Jets are quenched in heavy ion collisions far more than in simpler systems. The angular distribution of soft particles follows a harmonic signature that encodes the plasma's pressure gradients. Strange hadrons are enhanced as if the soup eases their birth, and heavy quarks, though massive, diffuse through the medium in ways that let us estimate how sticky the fluid feels to a traveler. The lifetime is unimaginably short, on the order of 10 to 20 femtoseconds divided by the speed of light, and the size is only a handful of femtometers across. But inside that blink and that droplet, a complete cycle unfolds. An initial glasma of intense fields, rapid thermalization, a period where fluid dynamics rules, and then hadronization as the expanding fire cools below the deconfinement threshold, and quarks relock into hadrons that stream to the detectors. None of this violates everyday experience so much as reframes it. The protons in your body are fossils from a later, cooler epoch of the same physics. And what we do in these colliders is momentarily lift the lid on an earlier chapter to read the script of strong interactions at their most honest. The applications are not power plants or weapons, but understanding, pinning down how a fundamental force behaves when pushed to extremes, testing ideas about minimal viscosity and collective behavior that echo in other fields from ultra-cold atoms to condensed matter, and refining models that feed back into cosmology's picture of how the young universe smoothed and cooled. There is no hype in admitting the limits. We cannot hold the plasma in a jar. We infer it from signatures and models that must be cross-checked from many angles, and we are still chasing a full map of the phase diagram at higher baryon densities, where neutron star interiors may live. But the core truth is firm and beautiful. By arranging a controlled catastrophe inside a magnet-lined tunnel, we create droplets of the earliest stuff and watch them behave like one of nature's most perfect liquids. We measure how they push on themselves and on anything that tries to pass through, and we learn from the way they fade. If there is a quiet human lesson here, it is that looking back toward the origin is not nostalgia, it is diagnosis. In the first microseconds, matter revealed its most basic temperament, and by recreating that temperament now, briefly and safely, we teach ourselves how complexity later emerged. You don't need to memorize the names of detectors or the alphabet of particles to feel the point. Inside a lab, we have found a way to make the early universe speak. And what it says is not chaos, but coherence. Not a gas of aimless constituents, but a liquid that remembers how to move together. And that memory, measured one collision at a time, is how we turn a flash of primordial heat into understanding. Superconductors at higher temps, chasing resistance-free wires. Imagine flipping a switch and having the current glide through a wire forever. No hum of wasted heat, no voltage drop sagging with distance, just a silent river of charge that never slows. This is the promise of superconductivity, and the chase for higher temperature versions of it is one of the most stubborn, exhilarating quests in modern materials science, because perfect conduction already exists, but only on nature's most specific terms, and engineers are trying to rewrite those terms without breaking the effect. At its heart, the phenomenon is simple to state and deep to explain. Below a critical temperature, certain materials abruptly drop their electrical resistance to effectively zero, and at the same moment, expel magnetic fields from their interior. A two-part transformation that tells you this isn't just better metal, but a new state of matter where electrons stop acting like independent, jittery particles and start moving as a coordinated whole. The orthodox picture for many conventional superconductors is that pairs of electrons, odd because electrons repel, form fragile partnerships by slightly deforming the crystal and using that shared vibration as a tiny handshake. And once they pair, these Cooper pairs behave like a single extended quantum object that can flow without being scattered the way lone electrons are, which is why a loop of superconductor can carry a persistent current for years without decay, and why a magnet hovers above a superconducting puck as if pinned to an invisible cushion of repulsion, a macroscopic wave organizing the microscopic chaos. But if you've noticed the catch, temperature, you've felt the central struggle. Most metals that become superconducting do so only when cooled near absolute zero, a realm of liquid helium and complex cryogenics. And while that's perfect, for the unwavering magnets in MRI machines or the intense fields in particle accelerators, it's impractical for reshaping the everyday grid. So the field has spent decades climbing the thermometer, first with alloys and compounds that nudge the onset a few degrees, then with a shock in the late 1980s when ceramic copper oxides, the cuprates, shattered expectations by switching with zero resistance at temperatures you could reach with cheap liquid nitrogen rather than delicate helium. Those materials, their family, are quirky heroes. They aren't metals in the usual sense. They're layered oxides with narrow planes where electrons interact strongly and don't behave like the gentle quasiparticles of simple metals. And the glue for pairing there seems to be rooted in collective motion rather than the gentle lattice handshake of the older theory, which is why, even after decades, a full microscopic consensus is still a live scientific conversation. Practical reality, though, is refreshingly concrete. That jump to liquid nitrogen temperatures opened a path to coated conductors, tapes of high-temperature superconductor grown in crystalline textures on flexible metal substrates, and those tapes now thread through high-field research magnets, compact power cables that snake under cities, and fault current limiters that act like fast circuit breakers for the grid, all because cooling to 77 Kelvin is comparatively easy, and zero resistance means a power line that laughs at ohmic losses, and a magnet that can be stronger without wasting energy as heat. The progress didn't stop with copper oxides. Iron-based superconductors arrived in the late 2000s, with more forgiving grain boundaries and intriguing physics of their own, and at the extreme edge a different family, hydrogen-rich compounds. Squeezed under colossal pressures, have displayed astonishingly high transition temperatures, even creeping up toward room temperature, but only while held in diamond anvils at pressures rivaling Earth's core, which makes them more like scientific beacons than immediate technologies. That contrast, materials that work in lab-friendly cryostats versus materials that break records under megabar pressures, defines the frontier. We know nature can make perfect conduction resilient at high temperature if the environment is shaped. Just so, but we're still learning how to stabilize such behavior without crushing the sample into submission. And along the way, the field has learned to be careful, because spectacular claims need equally spectacular verification, and the literature has seen both triumphs and missteps. Beyond temperature, two other limits shape what useful means. Superconductors hate large magnetic fields and large currents unless they're designed to handle them. And the way they fight back is by letting magnetic flux infiltrate in. Narrow threads, vortices that thread the material like tiny whirlpools, each carrying a quantum of magnetic field. If those vortices move, they dissipate energy and ruin the zero resistance promise. So material scientists litter the landscape with nanoscale pinning centers, defects, inclusions, tailored columns that grab vortices and hold them still, even as the current rises. And the success of modern tapes is largely a story of teaching the material to anchor those whirlpools while keeping the overall crystal coherent enough for the paired electrons to roam. This is also where the romance meets the workshop. Cuprate tapes are brittle ceramics layered on ductile metals, so making kilometers of wire means growing oriented crystals on textured templates, stacking buffer layers to bridge structural gaps, and controlling oxygen content to within tight margins. Because a little disorder can lower the critical temperature, shrink the maximum current, or cause the material to crack. Even so, the engineering is paying off. New magnets built from high-temperature tapes are pushing field strengths past what traditional niobium-based conductors can safely deliver. Fusion machines plan coils that need fewer tons of cryogenic infrastructure. Ship motors and aircraft concepts envision lighter, more efficient drives, and grid demonstrations show that a superconducting cable can carry the same power as a copper bundle 4 times thicker while barely warming the ground. Above it, the subtlety you learn after a while is that higher temperature doesn't mean no cooling. It means cheaper, simpler, and closer to every day. And that shift unlocks architectures that were too costly or too fragile before, replacing liquid helium baths with closed-cycle refrigerators, or even nitrogen baths, allowing devices to tolerate stop-start real-world conditions rather than pristine lab schedules. On the physics side, every new family of superconductor expands the menu of ways electrons can cooperate. Phonons in classic metals, spin or orbital fluctuations in correlated materials, potential mechanisms in hydrides under pressure, and each pathway whispers a hint about how to design the next compound. Which elements to mix, what lattice to build, what dimensionality to emphasize, what competing orders to avoid. There's caution on the horizon too. Alternating current introduces new losses as fields, and currents make vortices oscillate. Joints between tapes can become bottlenecks and refrigeration, while simpler still costs energy, so the systems that win are the ones where zero resistance plus strong fields or compactness beats the penalty of cooling by a clean margin. But step back, and the bigger picture is clear. In a century, we've gone from noticing a quirk of mercury at a few degrees above absolute zero to weaving kilometer-scale cables that carry thousands of amps with no resistive drop. From hand-waving cartoons of pair formation to sophisticated calculations and measurements that map the dance of electrons in exquisite detail, from cryogenic art to industrial practice. Perhaps the most thought-provoking part of this story is what it tells you about cooperation. When electrons that normally repel agree to move together, the world changes scale. Little imperfections stop mattering, and dissipation vanishes not because every collision is avoided, but because the collective state forbids the kind of scattering that causes loss. A reminder that sometimes the way past friction in your own work is not to polish every surface, but to find the pattern that makes friction irrelevant. So yes, higher temperature superconductors are still mostly cold by human standards, and room temperature, ambient pressure superconductivity remains a prize rather than a product. But the road already behind us powers hospitals, explores the subatomic world, trains magnets that may hold fusion plasmas steady, and lays test segments beneath our streets. And if you listen closely, you can hear the quiet promise that drives the field forward. One day, the wires humming behind your walls may not hum at all, and the silence will be the sound of a discovery, learning to live in the world. Strongly correlated electrons, when particles refuse to behave alone. Start with a rule you were probably taught without anyone saying it out loud. In a solid, each electron is a polite commuter that minds its own lane, zips past billions of neighbors, and, aside from a few gentle bumps with atoms, behaves as if it were alone. Now break that rule and you enter the world of strongly correlated electrons, where the crowd is the story, where every step an electron takes depends on what the others are doing, and where the simple add up the parts logic collapses into a tangle of collective behavior that can turn metals into insulators, insulators into odd metals, and ordinary crystals into arenas for phenomena that feel less like traffic and more like a murmuration that rewrites the sky as it moves. The cleanest way to feel what correlated means is to imagine trying to sit down in a packed theatre where every seat is reserved and the space between chairs is tiny. If you slide into one spot, you block someone else's path, and soon, the entire audience must rearrange, so a single motion triggers a chain reaction. In a metal where electrons barely notice each other, the standard playbook, treating them as independent quasiparticles that carry charge and heat, works brilliantly, a success called Fermi liquid theory. But in materials where the mutual repulsion is strong and the available seats, the atomic orbitals, are narrow, that playbook fails. Electrons don't glide, they jostle, hesitate, and sometimes freeze into patterns or refuse to move at all, even when classical reasoning says they should conduct. A paradox embodied by the Mott insulator, a crystal that ought to be metallic by electron counting, but locks up because trying to hop costs too much in crowding energy. The moment you dope such a system, adding or removing a few carriers, the crowd loosens in weird ways. And instead of a neat return to metallic calm, you may get strange metal behavior where the electrical resistance rises straight with temperature over astonishing ranges, as if each electron is always as entangled with the rest as the fastest processes in nature allow. A regime that seems to brush against universal Planckian limits on how quickly a system can shed coherence, and this linearity, seen in families, as diverse as copper oxide planes and twisted two-layer graphene with barely misaligned hexagons, is one of the starkest fingerprints of correlation. It announces that there is no single particle picture to fall back on. Correlations don't only jam motion, they reorganize identity. Heavy fermion compounds built from rare earth or actinide elements show low-temperature electrons that act hundreds of times heavier than a free electron, because local atomic moments and mobile carriers entangle into a composite fluid. So the effective mass swells not by adding particles, but by slowing their collective response, a feat measured in specific heat, magnetism, and quantum oscillations that reveal a large, Fermi surface counting degrees of freedom that seem localized at higher temperatures. In one-dimensional wires and chains, the breakdown is even sharper. Interactions shred the single electron quasiparticle into separate ripples of spin and charge, a Luttinger liquid. So what you inject at one end arrives at the other as split personalities that move at different speeds. A vivid example of how correlation can fractionalize what you thought was indivisible. In 2 dimensions, frustration and crowding can make charge bunch into stripes or crystals, ripple the lattice into periodic modulations, or twist the electronic fluid into nematic states that break rotational symmetry without changing. The underlying grid and the competition among these orders, the tug of war between wanting to align, to stripe, to flow, to localize, builds a phase diagram that looks more like weather than like a single season, with fronts and boundaries, and critical points where small changes in pressure, doping, strain, magnetic field, unleash sweeping reorganizations. Experiments have learned to listen to this complexity. Angle-resolved photoemission maps the momentum and energy of electrons as they leave a surface and shows when coherent peaks sharpen into well-defined quasiparticles or melt into broad humps that betray incoherence. Scanning microscopes draw charge patterns at the nanometer scale and reveal inhomogeneity that isn't mere dirt, but an intrinsic patchwork born from competing orders. Terahertz probes and optical conductivity track how the weight of electronic response shifts between low and high energies when a system crosses from itinerant to localized, a spectral weight transfer that is a hallmark of Mottness, and transport under extreme conditions, high magnetic fields that quantize orbits, high pressure that squeezes bandwidths, maps hidden Fermi surfaces, reconstructs them when symmetry breaks, and watches the approach to quantum critical points, where fluctuations of one ordering pattern grow so strong that they dominate physics across a whole swath of temperatures. Even the simplest classroom compounds reveal surprises once you tune them. Vanadium dioxide snaps from insulator to metal as it warms, and debate over how much of that jump is electron crowding versus lattice reshaping taught researchers to separate cooperative electron effects from structural ones. Layered nicolates and ruthenites let scientists dial correlations by swapping atoms, adjusting the width of electronic bands with chemistry rather than brute force, and exposing how small shifts in overlap control whether electrons lock or flow. And moiré materials, stacks of atom-thin sheets twisted by tiny angles, slow electrons by flattening their available energy landscape, turning mild interactions into decisive ones, and letting researchers move through a gallery of correlated states by turning a knob on a gate voltage. The practical why of all this is twofold. First, correlated matter hosts functionalities we cannot get from weakly interacting electrons, colossal responses to tiny stimuli, switchable phases, and, in some cases, pathways toward unconventional superconductivity and topologically non-trivial states that may one day encode information more robustly. And second, learning to design with correlations is a new engineering frontier, much as learning to design with band structure transformed electronics in the last century. Honest limits, however, keep the field grounded. Correlation-friendly materials are often brittle, sensitive to disorder, and complex to make. Measurements are delicate, and models are hard because the crowd won't let you split the problem into neat one-body pieces. And even the most celebrated phenomena live amid competing effects that must be disentangled patiently to avoid overpromising. Yet there is clear progress. Theories that blend local realism with itinerant motion, dynamical mean field approaches, and their cluster cousins now reproduce phase boundaries and spectra that match experiments, algorithms on quantum devices, test toy versions of correlated Hamiltonians to validate intuition, and data-driven searches sift chemical space for compounds with the right balance of bandwidth and repulsion before anyone lifts a crucible. The deeper human meaning is that correlation is neither a bug nor a miracle. It's what happens when the cost of ignoring your neighbors is too high. So the system invents new collective identities that none of the parts possessed alone. And if you carry that back to your own thinking, you'll recognize the same pattern in teams that outperform the sum of their members, and in crowds that stall when coordination fails. When particles refuse to behave alone, they teach you a more honest definition of order. Not a tidy line of obedient individuals, but a dynamic agreement forged under pressure. Fragile in detail, yet powerful in effect, capable of turning the same lattice into a conductor, an insulator, or something in between, simply by changing how everyone listens to everyone else. And as you let that sink in, remember that the most interesting materials of the next decades may not be those with the cleanest solitude, but those with the richest conversations. Solids where electrons negotiate constantly, share momentum, like whispers, and, in doing so, open doors to properties we didn't know a crystal could have. Majorana modes, quasi-particles that are their own antiparticles. Try to imagine a quantum state that looks in a mirror and sees no opposite, no distinct antiparticle to cancel it, just itself, perfectly symmetric between being an electron and being a whole. And then imagine that this state doesn't roam the bulk of a material, but anchors itself at special places like the end of a nanowire or the core of a vortex, sitting right at zero energy, like a book wedged into the exact middle of a shelf so it cannot slide left or right. That is the intuition behind Majorana modes in solids. Not fundamental particles flying through space, but emergent quasiparticles in certain superconductors, where the collective dance of many electrons conspires to create excitations that are their own antiparticles. And what makes them more than a curiosity is how they might store and manipulate quantum information in a way that naturally resists many of the small errors that plague ordinary qubits. To understand how such an odd creature can appear, start with superconductivity's most basic gift. At low temperature, electrons form pairs that blur the line between particles and holes, so a tiny push on the system can create an excitation, with some electron character and some hole character mixed together. In most superconductors, that mixture still sums to something that behaves like a usual quasiparticle. But in special conditions, when superconductivity is combined with strong spin-orbit coupling and a magnetic field, or with a magnetically ordered texture, the mixture can be tuned so perfectly that the excitation becomes exactly half and half, a state that is mathematically real rather than complex, and thus identical to its own charge conjugate twin. In practice, you don't hunt for this by waving equations, but by building hybrids. A narrow semiconducting wire with strong spin-orbit interactions is laid on a superconductor so that pairing leaks into the wire. Then a magnetic field splits the spin states just enough to tip the system into a topological phase, and if disorder is tamed and the parameters land in the right window, theory says a Majorana mode should appear at each end of the wire, two halves of a non-local fermion, whose information is stored in their joint parity rather than at a single spot in space. What would you see if you probed one end gently with a tunneling contact? You would measure a spike in conductance right at zero bias, a sign that the mode sits at zero energy and invites perfect Andreev reflection, where an incoming electron is reflected as a whole with certainty. You would also look for a Josephson junction that reveals a periodicity twice as large as usual, a fingerprint of the mode's unusual relationship to phase. And you would try to show that the two ends talk to each other coherently over long distances, because the whole point is that the qubit is written across the pair, not etched into either end alone. Across the last decade, labs have chased precisely these clues in a variety of platforms. Semiconductor, superconductor nanowires, where gate voltages and fields can be tuned in real time. Chains of magnetic atoms assembled on a superconductor's surface where the magnetic pattern seeds a topological band inside the energy gap. Vortices in certain two-dimensional superconductors where the swirling order may trap a zero-energy core state. And engineered junctions on the surfaces of materials with strong spin-orbit coupling that promise the right symmetry to host robust edge modes. The drama of the search is part of the lesson. Experiments have seen zero bias peaks that look promising. They have reported missing steps in microwave-driven junctions and other suggestive signatures. But they have also learned how easily more ordinary states can impersonate a Majorana. Disorder can trap near-zero energy Andreev-bound states that mimic the same tunneling spike. Inhomogeneous potentials can split and rejoin levels in ways that trick simple tests, and finite temperature or soft gaps can wash out the very quantization you want to claim. So the community has steadily raised the bar, asking not just for a peak, but for a robust, quantized peak. Not just for a local feature, but for non-local correlations between the two ends. Not just for a gapless mode at one field angle, but for a full set of behaviors that hang together across many knobs. You might wonder why this matters so much beyond the thrill of finding a textbook idea in the lab. And the answer is wrapped up with a phrase that sounds like science fiction, but isn't. Non-abelian statistics. In ordinary life, swapping two identical objects does nothing, and in ordinary quantum systems exchanging particles only adds a simple phase factor. But in a world with Majorana modes arranged around a network, exchanging, or braiding, the modes actually rotates the system's quantum state in a way that depends on the order of the swaps. It is like tying a knot in a cord, rather than just flipping a light switch. The history of the motion is stored in the final configuration, and that history can encode quantum information in a way that is naturally protected against many local disturbances, because a small nudge at one location cannot, by itself, untie a global knot. In two dimensions, you picture moving vortices around one another. In one-dimensional wires, you use T-junctions, where gating paths on and off lets two end modes pass and exchange positions without ever meeting. And in both cases, the dream is a topological qubit, whose basic operations are geometrical paths rather than delicate pulse sequences fine-tuned against every noise source in the room. You won't hear dishonest promises here. No lab has yet demonstrated full braiding with unambiguous topological protection, and some early headline results have been reconsidered after deeper analysis, which is exactly how careful science should work. Instead, what has grown is a more rigorous checklist. Prove that the zero bias peak is quantized and stable across parameter sweeps. Show that it splits and rejoins as the two ends hybridize and then separate. Demonstrate that parity readouts at opposite ends are correlated in the way a shared non-local state demands, and eventually carry out exchange operations that follow the non-abelian rules rather than the algebra of ordinary bound states. Alongside this push have come engineering advances that sound mundane, but are transformative. Cleaner interfaces that produce a hard gap with far fewer stray states. Epitaxial growth that eliminates the oxide mess at metal semiconductor junctions. Improved dielectrics and gating that make the potential landscape smoother, and layouts that keep stray magnetic fields where they belong, all of which nudge real devices toward the idealized models in which Majorana modes are easiest to see. Meanwhile, theorists have sharpened the alternative explanations so experimentalists know exactly what to rule out, suggesting cross-checks based on how signals scale with temperature, how they respond to subtle patterning of the superconducting phase, and how deliberately added impurities should or should not disturb a truly topological mode. The reason this story belongs in your mental toolkit is that it shows how a simple idea, a quasiparticle that is its own antiparticle, can reshape an entire strategy for computation and measurement. Information that lives non-locally is harder to poke accidentally. Operations that are tied to braids rather than pulses are harder to scramble. And devices that exploit geometry rather than perfection can, in principle, thrive in the messy real world. Even if topological quantum computing ultimately blends Majoranas with more conventional qubits, the pursuit has already paid off by forcing us to master cleaner materials, clearer diagnostics, and more honest standards of proof. And there is a human echo worth noticing. When you split a single identity into two halves that only make full sense together, you create resilience. The story cannot be told from one end alone. The meaning is in the connection. And that is the quiet philosophy running beneath the physics. Majorana modes are not magic. They are what happens when a many-electron system is tuned so that symmetry, pairing, and spin-orbit coupling intersect just right. And if you build patiently, test skeptically, and read both the local and the non-local signs, you can coax a piece of the quantum world into revealing a new kind of stability, one that might one day help your most delicate computations survive outside the safe walls of a lab. Optical lattices, pinning atoms with light. Imagine drawing a crystal with nothing but laser light. No atoms fixed in a solid. No chiseling of a lattice into a chip. Just beams crossing in space to paint a standing pattern of bright and dark that quietly persuades free atoms to sit down on invisible seats. That is an optical lattice, a playground where light itself pins matter. And once you feel how it works, the rest of the magic follows naturally. Counter-propagating lasers interfere to make a row of bright crests and dark troughs spaced at about half a wavelength, and neutral atoms cooled to a crawl. Feel those ripples as hills and valleys in their energy. Choose the color of the light, a little red of an atomic resonance, and the atoms are drawn to the bright spots. Choose it a little blue and they flee to the dark. A simple, tunable rule, born from the way an oscillating field shifts an atom's levels, the same effect that gives optical tweezers their grip. And with one dimension mastered, you add more beams to knit 2D grids or full 3D egg crate traps, or even get clever with angles to make triangles, honeycombs, and superlattices with alternating deep and shallow wells. The upfront surprise is that this crystal of light gives your gas of atoms a band structure the way a real crystal gives electrons one. There are allowed and forbidden energies. Tunneling between sites plays the role of electronic hopping, and the geometry of the pattern decides how easily particles move. So by changing beam intensity, you literally turn a knob labeled "How tight is the lattice?" And by changing the spacing, you set the scale of the whole experiment. When the lattice is shallow, atoms tunnel freely and phase lock across many sites, giving you a coherent superfluid that leaves sharp interference peaks when you switch the trap off and let it expand. A fingerprint you can catch with a camera, but as you crank the light higher, the wells deepen, tunneling slows, and interactions finally win, pushing the system into a Mott insulator where each site holds an integer number of atoms and long-range phase coherence collapses. No crystal of matter, still just light, but a clear phase transition you can watch with your eyes in the momentum pattern. The power of this platform is the clarity of its controls. You set the lattice depth with laser power. You set the pressure of the gas with overall trap strength. You tune interactions with a magnetic Feshbach knob that nudges scattering from weak to strong. And you choose the lattice geometry as if you were sketching a board game, square for simplicity, triangular to frustrate motion, honeycomb to mimic graphene's cones. And then you study how matter responds, not in a computer, but in a clean, tabletop quantum simulator that solves models identical to those used in theories of magnetism and high-temperature superconductivity. Because the atoms are neutral, you might think you can't teach them about magnetic fields, but light steps in again. By shaking the lattice just so, or by imprinting phases on tunneling links with additional beams, you synthesize gauge fields that make atoms behave as if a magnetic flux threads each plaquette, letting you explore Hofstadter butterflies, chiral edge motion in topological bands, and other phenomena once confined to electrons in strong fields. Except here there's no disorder from a dirty crystal, and you can dial the effective field to values impossible in solids. All of this would be hand-waving if you couldn't see it. So the field built microscopes that image single atoms on single sites, quantum gas cameras that peer through the glass and resolve a checkerboard of occupation with enough fidelity to observe patterns of antiferromagnetism in fermionic gases and the birth of correlations one link at a time. Tilt the lattice slightly so gravity adds a uniform pull, and you'll watch block oscillations, a graceful sloshing in momentum space that textbooks once framed as a curiosity for electrons, but which solids rarely reveal because of scattering, while ultra-cold atoms perform the motion cleanly on demand. Add a calibrated splash of disorder, speckle light, or a second incommensurate lattice to mimic a rough landscape, and you can push the gas into regimes of localization where transport stalls, then back it out again to map where the line between fluid and arrested dynamics really lies. Beyond many-body physics, optical lattices also power precision. In an optical lattice clock, strontium or ytterbium atoms are held at a special magic wavelength that shifts two clock states equally, freezing out motion while preserving a pristine reference transition whose tick now ranks among the most stable in science, precise enough to sense the change in gravitational potential across a lab bench. If you want applications, they are honest and present. Clock networks that compare time across continents and test fundamental symmetries, inertial sensors that use coherent matter waves climbing a tilted lattice as exquisitely sensitive accelerometers, and a new generation of quantum simulators that attack models of electrons in moiré materials, strange metals, and frustrated magnets with real-world knobs and real-time movies, while the dreamier promises, like universal quantum computers built solely from lattice-bound atoms, are being pursued in parallel with arrays of individually controlled tweezers that can merge with lattice techniques to get the best of both worlds. There are limits you should know. Heating from off-resonant scattering sets lifetimes, laser noise jitters the potential, and reaching the lowest effective temperatures, where fragile orders blossom, demands careful entropy management, often by rearranging traps to park heat away from the region you care about. But these are engineering challenges, not fundamental roadblocks, and with each year the coherence times lengthen and the images sharpen. The deeper lesson is conceptual. By shaping the environment with light, you can make matter adopt behaviors it would not choose on its own, and you can do it with transparency. Every parameter visible, adjustable, testable, so the claims stand on more than pretty pictures. An optical lattice is a patient invitation to atoms. Here are the seats, here are the aisles, here is the rhythm of the hall. Show me what your rules make of this room. And in the answer, you don't just reproduce the behavior of electrons in a crystal, you gain the ability to ask counterfactual questions. What if the lattice were perfectly clean? What if the field were enormous? What if the interactions were twice as strong? With the confidence that the experiment will listen. And when the cloud finally dims and the beams switch off, the question that lingers is simple and profound. If light can write crystals, then design of fields, of geometry, of constraints, is as fundamental a lever on nature as composition. A reminder that in physics, as in life, the patterns you project can be just as decisive as the parts you start with. Cavity QED, trapping light to tame matter. Picture two mirrors facing each other so perfectly that a single photon can ricochet between them thousands, even millions of times before escaping, and now slip a single atom, or a quantum dot, or a superconducting qubit into that tiny stage, so the light has no choice but to keep meeting the same actor again and again. That is the essence of cavity quantum electrodynamics, a discipline that does something quietly radical. It changes what empty space means for an atom by redesigning the very room where it emits and absorbs light, and in doing so, it lets you speed up, slow down, or even choreograph interactions that in the open would be random and forgettable. Start with the simplest truth. An excited atom in free space will eventually glow and relax. But inside a high-quality optical cavity, the rules bend, because the mirrors pick out a few favored modes of the electromagnetic field and suppress the rest, turning the usual sea of options into a small set of resonant notes, and the atom happily sings louder if its transition matches one of those notes and stays oddly quiet if it doesn't, an effect known as Purcell enhancement, and its mirror image, inhibition, both of which come from the same idea. By changing the available states of light, you reshape what spontaneous means, push the confinement harder, tighter mode volume, better reflectors, cleaner alignment, and you cross into strong coupling, a regime where the atom and the cavity stop being separate personalities and trade energy back and forth faster than either one leaks it away, producing a hallmark signature called vacuum-Rabi splitting that you can literally see as a doublet in the spectrum. When you look through the mirrors, two hybrid peaks that announce the birth of dress states made of atom plus photon together, rather than either alone. This back-and-forth swapping can be watched in time as an excited atom dims while the cavity brightens and then re-brightens as the photon returns. A coherent exchange that turns a single quantum into a pendulum. Once you can trap light like this, you can tame matter in ways that sound like science fiction, but live on lab benches. Send in a faint laser, and because your single atom saturates easily in the tight field, the cavity admits at most one photon at a time, a phenomenon called photon blockade that turns the whole device into a sub-microscopic traffic light for light itself. Flip the story, and you can make a single atom act as a mirror. Depending on its internal state, it will reflect or transmit a weak probe, which means one qubit of matter can switch a stream of photons on command, a primitive for quantum routers, and gates that don't need bulky crystals or huge powers. With several atoms in one resonator, you can mediate interactions at a distance, stitching entanglement between particles that never touched because each one touched the same handful of trapped modes, and with a string of cavities linked by optical fiber, you sketch the blueprint of a quantum network where information moves as single photons but is stored and processed in protected matter states. None of this asks you to memorize equations. Just carry two rates in your head. How fast the atom talks to the cavity and how fast each leaks energy. When the talking beats the leaking, coherence wins and you get clean hybrid physics. When leaking dominates, you're still in a useful regime because the cavity can serve as a loudspeaker, making the atom's faint whisper detectable without blasting it apart, the foundation of gentle readout techniques that approach see without breaking, where you infer an internal state from a tiny shift in the cavity's resonance rather than by grabbing the atom directly. There isn't just one kind of cavity, and that diversity is the secret to turning principles into tools. You can use centimeter-scale Fabry-Perot mirrors with astronomical finesse for single neutral atoms, sculpt photonic crystal nanobeams that trap light in volumes smaller than a cubic wavelength and marry them with embedded quantum dots on a chip, guide photons around whispering gallery microdisks, or, at lower frequencies, build microwave resonators from superconducting metal and couple them to artificial atoms called transmons, the workhorse of circuit QED, where the same Hamiltonian plays out in a different accent. That last platform has already delivered practical payoffs. High-fidelity readout that barely disturbs the qubit, tunable coupling that can be switched on for fast 2-qubit gates and off for storage, microwave photons routed on chips like tiny, male, and protected cat states, superpositions of different cavity fields that store quantum information in a way that smears error across many photons and makes it easier to catch and correct. Back in the optical world, cavity-enhanced single photon sources have become reliable enough to feed photonic quantum computers and secured link experiments, while cavity-stabilized lasers set the ticks of the world's best optical clocks by locking their color to a line as narrow as nature will allow. Even metrology benefits at a deeper level. By folding many atoms into the same resonator, you can measure a collective property more precisely than quantum randomness would normally permit, creating squeezed states that sharpen frequency standards and magnetometers without adding more particles. It's worth being honest about edges. The very mirrors that trap light also collect dust and drift. Vibrations blur alignments, materials absorb and heat, and for quantum dots or color centers in solids, the surrounding crystal can jitter the energy levels unless you grow and process with obsessional care. Nevertheless, the direction of travel is steady: higher mirror quality, smaller mode volumes, quieter environments, better interfaces between atom and device, and each improvement pays twice because it boosts both the control you have and the gentleness with which you can exercise it. If you like a unifying picture, think of cavity QED as architecture for the vacuum. You decide which rooms of the electromagnetic mansion are open, which doors are shut, which corridors connect, and then you invite matter inside to see how it behaves in your custom house, discovering in the process that spontaneous emission is not fate, but a design variable, and that the strength and character of a single photon atom meeting is something you can dial. And if you want a human echo, let it be this. We spend much of life trying to change the actors, the materials, the people, the conditions, when often the wiser move is to change the room, to design the environment so that the right interactions happen more often than the wrong ones, the way mirrors coax a reluctant atom to speak clearly or hold its tongue. Trapping light to tame matter is physics, yes, but it's also a philosophy of gentle leverage. Shape the space, slow the chaos, and even fleeting quanta will learn to keep time with you. Quantum non-demolition measurements. Seeing without breaking. Imagine being able to look at a fragile quantum system and learn exactly the thing you care about. How many photons are in a cavity or which way a qubit points, without knocking. The value around or burning the evidence in the very act of looking. That is the promise of quantum non-demolition measurement. A careful way of asking a question so the answer can be read now, read again later, and even used to guide the system in real time, all while the damage that measurement inevitably causes is shunted into a place that doesn't spoil the value you're tracking. To feel why this is remarkable, remember the usual fate of measuring at the smallest scales. Detectors gulp photons to register a click. Atoms fall from excited states when you interrogate them, and pushing on a tiny oscillator to see where it is ends up jostling it so much that the next look is about a different motion than the one you started with. QND turns that around by choosing both the quantity to be read and the way the probe couples to it, so that the unavoidable back action is steered into a conjugate property you've decided not to care about, which means repeated questions return the same answer within the system's natural evolution, rather than an answer mangled by your curiosity. In practice, this takes many forms, each tailored to a platform, but all sharing the same spine. If you want to count light without eating it, you don't put a photodiode in the way. You let the light sit between mirrors and slip a gentle atom or artificial atom through, arranged so that the presence of n photons nudges the atom's energy by a tiny countable amount, a shift you read out later without removing the stored light. Do this carefully, and you can watch the number rise, and fall one quantum at a time, even witness the field losing a photon to mirror loss without your detector being the thief. If you care about the orientation of a collective spin in an atomic cloud, you don't blast it with a beam that flips the very spins you are trying to survey. You pass a dim, detuned pulse whose polarization twists proportionally to the spin component you've chosen, and because the light barely talks to the orthogonal component that carries the quantum noise, your back action lands there instead, leaving the monitored projection available for a second and a third look. This trick, repeated across an ensemble, can squeeze the noise of the measured component below what uncorrelated atoms would allow, sharpening magnetometers and clocks without adding particles. For tiny mechanical objects where position and momentum are in delicate balance, you can evade the worst of measurement recoil by arranging to read only one quadrature, one slice of the motion's cycle, at stroboscopic moments when the probe couples to that slice but not its partner. So the kicks you deliver accumulate in the unmeasured quadrature while your chosen one stays clear, a strategy that lets you approach sensitivities once thought off limits. Even the most ambitious observatories on Earth rely on these ideas. Kilometer-scale interferometers that listen for the ripples of distant black hole mergers are limited by the jitter of light itself, so they reshape the quantum fluctuations of the laser with squeeze states, put their meters on the output quadrature that carries the signal, and divert the measurement's fury into a channel that doesn't hide the wave they want to hear. This is QND thinking writ large, a way of organizing the quantum noise so the universe can speak. In quantum computing, the same philosophy has become essential plumbing. Rather than blasting a qubit with a resonant pulse that knocks it off state, circuit devices read the tiny color shift a qubit induces on a nearby resonator, and because the readout couples to which state are you in rather than to a flip operator, the answer sticks long enough to be error-checked and corrected while the computation continues. What separates all these successes from wishful marketing is a simple checkpoint. If the measurement is truly non-demolishing for the chosen variable, doing it twice in a row, quickly, should give the same result up to known dynamics, and the very act of learning the value should not increase the spread of outcomes when you repeat the same measurement immediately afterward. Meeting that standard is hard. Stray couplings leak back action into the quantity you wish to preserve. Finite temperature burps random energy into the system. Technical noise disguises itself as quantum inevitability. So experiments earn the E label by showing stability across parameter sweeps, by proving that the information comes out through a channel predicted to be harmless, and by demonstrating that the readout can be used for feedback. Cool a mechanical mode closer to rest by always nudging opposite the measured motion, or stabilize a qubit by quickly correcting rare flips you discovered without causing them. It's worth separating QND from two neighbors that often get conflated. One is gentle probing that simply uses fewer photons or lower power. Useful. But if the coupling dumps disturbance into the very thing you care about, it's not non-demolition, it's just soft. The other is the freeze you get by watching constantly, sometimes called the Zeno effect, where frequent, strong projective measurements keep a system stuck in place. Not what we want here, because QND is about learning repeatedly without pinning the system with brute force, preserving the dynamics you want while tracking a specific constant of motion or a protected observable. The payoffs reach far. In metrology, QND readouts paired with squeezed inputs improve the precision of clocks, magnetometers, and interferometers beyond the usual counting limits. In networks, QND interactions can entangle distant nodes by measuring joint properties, parities, and sums without learning the private value of any one node, a cornerstone for error correction and secure distribution of quantum states. In fundamental studies, QND counters catch rare events in flight, a single phonon exchanged, a quantum jump in a field, transforming statistics into movies rather than after-the-fact snapshots. The honesty, though, is that making an observable immune to your touch is never absolute. Every apparatus has leak channels, every constant drifts if the Hamiltonian shifts, and designing the coupling so that the measurement operator truly commutes with the system's natural evolution can be like threading a needle in a windstorm. Yet the discipline of trying delivers enormous practical gains because even partial non-demolition lets you chain measurements, average out noise, and close the loop with feedback that would be impossible if each glance smashed the very thing you wanted to keep. The deeper lesson, and the reason this belongs in the way you think about knowledge, is that the cost of information depends on what you ask and how you ask it. In the quantum world, there is no free lunch, but there are smart menus. And by aligning your question with the system's protected directions, you can learn richly without burning the subject. That is why seeing without breaking is more than a slogan. It is a design principle that turns measurement from a destructive spotlight into a reversible conversation, and it suggests a way to handle delicate things beyond physics too. Pick the aspect you need to know. Design your interaction so your curiosity pushes on something else, and you'll be able to look again and again until the picture becomes clear without ever losing the subject you set out to understand. Rydberg polaritons, hybrid light matter creatures. Picture a single photon entering a quiet cloud of ultra-cold atoms and, instead of flashing through at light speed, slowing to a walking pace and borrowing a body, half wave, half matter, so that it can feel the presence of another photon meters away. That borrowed body is a Rydberg polariton, a hybrid creature stitched from a faint pulse of light and a collective twist of many atoms. And it exists because you arrange the atom's energy levels so that a weak probe beam that would normally be absorbed is made transparent by a second control beam in a trick called electromagnetically induced transparency, but with a decisive twist. The upper state you use is an enormous Rydberg level, whose electron is so far from the nucleus that neighboring atoms can sense it, which means the presence of one polariton shifts the energy landscape for others and turns normally indifferent photons into strongly interacting actors. The simplest way to feel this is to imagine the light's identity being shared. Part of its amplitude remains a photon gliding through space. Part becomes a spin wave stored across thousands of atoms. So when you reduce the control field, the polariton's photonic piece shrinks and the matter piece grows, slowing the pulse to a crawl and even letting you stop it entirely and hold it as a pattern of atomic correlations. Then restart it later to let the photon fly again. A reversible translation between flying information and stored memory. Now bring in the Rydberg twist. Because atoms in a Rydberg state repel or attract each other extremely strongly over micrometer distances, a single stored excitation carves out a blockade region around itself where no other atom can be put into the same Rydberg level, and that condition feeds back to the passing light by closing the transparency window locally. So a second polariton that enters this zone suddenly finds the medium opaque or phase shifted and is forced to change, course or timing. With the right detunings and powers, that blockade region becomes a movable exclusion bubble carried by the first photon's matter half. And the result is a non-linearity at the few photon level that conventional optics cannot touch. 2. Faint. Beams that would normally pass through each other like ghosts now scatter, delay, bind, or even repel in ways you can dial from attractive to repulsive with a knob. This is not metaphor, but laboratory routine. Experiments send in a weak stream of source photons and a single gate photon stored as a Rydberg spin wave. Then release the control field to test how many source photons make it through, and the answer changes dramatically depending on whether the gate was present. One stored excitation can switch or attenuate hundreds of passing photons, a microscopic transistor where the gate is literally a lone quantum of light. Other groups watch the statistics of outgoing photons and see fingerprints of strong interactions. Anti-bunching, where photons avoid arriving together because the first one's blockade makes the second wait, or bunching, where an engineered attraction makes them leave as bound pairs, sometimes called photonic molecules, whose joint wave packet behaves like a single object with a mass and a size you can tune by adjusting the atomic parameters. Yet others measure the phase shift that one photon imposes on another and push toward the holy grail of a full pi shift. Enough to make a two-photon logic gate, which would allow all optical quantum computing where the qubits are flying light, pulses that compute by briefly donning matter cloaks to talk. Under the hood, the language that ties these phenomena together is pleasantly physical. The more you mix light into matter, the slower the polariton moves and the longer it lingers near its partners, which amplifies interactions. The stronger the Rydberg character you borrow, the larger the blockade radius, the keep-out zone, that each polariton drags along. And the narrower and cleaner your transparency window, the less loss you suffer as these delicate excitations weave past one another. The knobs are practical ones: laser color and power to set the transparency and the group velocity, choice of principal quantum number to set the interaction, strength, atomic density, to ensure that within each blockade sphere there are enough atoms to build a crisp collective state, and temperature and shielding to stop stray electric fields from tugging on the giant Rydberg levels and smearing your control. With those knobs tuned, the platform turns into a quantum materials lab for light. You can realize gases of photons whose behavior maps onto famous models of interacting particles, from fluids that act almost collisionless to regimes where the repulsion is so strong that the photons mimic a hardcore gas, and you can dial from attraction to repulsion to sculpt-bound states, soliton-like propagation, and even topological band structures when you add spatial patterns and motion to the beams. If you want a visual, think of a narrow optical fiber filled with cold atoms or a free space beam threading a magneto-optical trap. The incoming photon enters, becomes partly atomic, slows to a pace of meters per second, senses another polariton's keep-out bubble, and either skirts it, sticks to it, or passes through with a controlled phase delay depending on your settings, all while the atomic ensemble remembers the encounter as a tiny, reversible change in its shared state. Because the hybrid is part light, you can route it over long distances with low loss and read it out with exquisite sensitivity. Because it is part matter, you can stop it, store it, and make it feel forces that pure photons ignore, like the proximity of a second Rydberg spin wave. That dual citizenship is why the idea has legs far beyond curiosity. Single photon switches and transistors point to energy-efficient repeaters for quantum networks, where you do not blast signals with amplification, but gently control them with other single photons. Few photon phase gates promise modular optical processors, and reconfigurable quantum memories let you buffer and synchronize flying qubits so distributed computations can unfold in step. Even sensors benefit, because a single polariton's frequency shifts when local fields or nearby charges perturb the Rydberg state. A carefully prepared ensemble becomes an ultra-sensitive antenna that reads electric environments with quantum-limited precision, turning every stored photon into a field meter. Honesty matters as much as excitement, and the limits are clear. The Rydberg states that give you strength also decay and dephase. The atomic motion that is negligible at microkelvin temperatures becomes a nuisance in warmer vapors. Residual absorption in the intermediate level eats your signal if the transparency isn't clean. And making the blockade sphere large while keeping loss small is a balancing act that demands high optical depth and stable lasers. Yet each year the engineering inches forward. Better electrodes that tame stray fields, cryogenic or ultra-cold setups that stretch coherence, hollow core fibers that confine both atoms and light for long interactions without diffraction, and clever pulse shapes that trade a little speed for a lot of fidelity. So the same basic recipe that seemed audacious a decade ago now supports stable demonstrations across labs. What you should carry away is a change in how you think about light. Photons aren't condemned to pass through one another unnoticed. They can be given temporary bodies that let them collide, stick, steer, and compute, provided you lend them an atomic crowd to inhabit. In that sense, Rydberg polaritons are a parable about context and cooperation. The beam learns to feel because it shares itself with matter. The atoms gain new roles because they share themselves with light, and together, they create a domain where information can move and interact softly rather than violently. When you hear hybrid light matter creatures, don't imagine a slogan. Imagine a discipline where gentleness is power, where a single stored quantum can redirect a river of others, and where the future of optical technology may look less like blasting signals through glass and more like persuading whispers to talk to whispers by briefly giving them hands. Ultra-cold chemistry. Reactions near absolute zero. Imagine cooling a room until motion itself seems to hush. Gas becomes a mist of gentle possibilities. Molecules slow from frantic ricochets to hesitant meetings, and something ordinary but invisible in daily life finally takes the stage. Chemistry that runs on quantum rules rather than heat. Ultra-cold chemistry lives within millionths or billionths of a degree above absolute zero, where collisions are so slow that particles sense each other as waves with sizes larger than the molecules themselves, and that change flips the script you learned in school. No more chaotic scrambling over barriers, no more averages over a swarm of speeds, but collisions that are choreographed by symmetry, by the exact internal states you set, and by fields you dial from outside, like a careful conductor. To get there, researchers first tame atoms with laser light that nudges them against their own glow until they crawl. Then stitch pairs of these rested atoms into molecules in chosen quantum states using magnetically tuned encounters and gentle two-color pulses that slide them to their ground configuration without heating. Or they cool certain simple molecules directly, species like, say, AF, SRF, or YO, whose internal structure plays nicely with laser cycling, before gathering them in. Magnetic or optical traps, once captured, the laboratory turns into a kind of chemistry theatre where you choose the cast. Bosons or fermions, reactive or non-reactive, the stage, a three-dimensional bowl of light, a two-dimensional sheet, or a one-dimensional tube, and the soundtrack, electric or microwave fields that orient dipoles, lock rotations, or even shield against loss. And then you let pairs meet while cameras watch individual events unfold, rather than only tallying products long after the fact. What makes the reaction strange is how much of the usual playbook disappears. At room temperature, the fastest molecules climb over energy barriers with thermal kick, but near absolute zero there is almost no kick to spend, so outcomes are steered by tunneling through barriers, by resonant pauses where a transient complex lingers like a held note, and by threshold rules that say which collision channels are allowed at vanishing speed, if the partners are identical fermions in the same internal state. For instance, the simplest head-on approach is forbidden by symmetry. So the first allowed path carries an angular momentum barrier that suppresses reactivity unless you coax the geometry just right. That sensitivity becomes a tool. Line up polar molecules with a gentle electric field so their dipoles face side by side and watch reactions fade. Tip the field so they approach head to tail and watch rates surge. Press them into a flat optical lattice and see once dangerous encounters vanish because the harmful alignment is no longer available. Then add microwaves to dress their levels and create a repulsive halo that keeps them apart unless you want them to touch. Even the meaning of reaction rate changes character. Rather than a blur of speeds, you measure how a single well-prepared population dwindles in time. Or you count products one by one with state resolution, catching, for example, two atoms, merging into a molecule, and then that molecule quietly disappearing into a long-lived complex that wanders before it flies apart. Some systems are universal, reacting as soon as they reach short range regardless of the details, while others are sticky without reacting, forming loitering complexes that tie up your sample until tiny perturbations kick them free. Either way, the physics teaches you which knobs matter for control. With these knobs, cold chemistry becomes a laboratory for ideas long dreamed about. Make two atoms meet in known spins and rotational states, and ask, pathway by pathway, which exit channels they choose. Engineer bound pairs of photons stored in a cloud of atoms through other tricks, and watch them scatter off a single molecule you've pinned and oriented. Build an array of individual atoms or molecules in optical tweezers, tiny cups of light you can move, and pull two cups together to witness a single encounter while counting every possible outcome. Then repeat thousands of times to sculpt statistics from identical trials rather than from a thermal mush. And because the samples are gentle and pure, you can use the same platform for precision measurements. Molecules are exquisitely sensitive to small symmetry-breaking effects, so the same control that lets you decide whether A meets B also lets you test whether nature hides a tiny electric dipole inside the electron, or whether fundamental constants drift over time, with chemistry acting as the meter rather than as a complication. Not all of the surprises are soft. Cold ions held in electromagnetic traps collide with ultra-cold neutral atoms and show regimes where a centuries-old capture model, once a baseline estimate, gives way to quantum structure in the cross-section. Peaks and valleys from long-range potentials that only appear when motion is slow enough to notice. And even simple three-body processes, where a third partner steals away energy to let two bind, follow rules that can be tuned by adjusting the scattering. Properties with fields. Is this useful beyond curiosity? In the near term, yes, because learning to suppress or enhance loss keeps quantum simulators and quantum computers alive longer when their building blocks are molecules. Because state-selective reactions at low energy could enable analytic chemistry that reads identities by watching which ultra-cold pathways light up. And because the same control may help assemble complex structures one bond at a time, not by tossing reagents together, but by positioning and addressing partners like pieces on a board. Honesty runs through the field too. Cooling molecules is still hard, lifetimes are finite. And the most flexible control often lives in small samples where every photon, collision, and stray field must be managed with care. Yet year by year the toolkit expands. Better laser-coolable species, hybrid traps that merge electric and optical control, microwave shielding that turns reactive pairs into long-lived dipolar fluids, and detectors that resolve not just did it react, but which rotational note did the product leave singing. If there's a deeper lesson, it's that temperature is not just a number on a thermostat, but a regime of truth. Lowering it peels away the thermal noise that hides the logic of interactions and reveals how much of chemistry is geometry, symmetry, and timing. How much is choice rather than chance once you slow the movie enough to direct it. And that lesson travels. You don't need to live at a billionth of a degree to borrow the mindset of ultra-cold chemistry. Define the states you care about. Choose the geometry that avoids harmful encounters. Use gentle fields to steer rather than shove, and track outcomes with the granularity that lets you learn from each event. Near absolute zero, reactions show you their bones, and in that clarity, you see a path from spectacle to craft, from watching nature's heat-driven habits to composing its quiet, quantum-tuned conversations. Levitation by diamagnetism, floating with graphite and fields. Tilt a magnet over a thin tile of graphite and notice something your instincts don't expect. The tile refuses to settle onto the magnet's face, instead hovering a millimeter above it, sliding as if on invisible rails, and then coming to rest with a stubborn, gentle float. No tricks, no hidden coils, just carbon and a static magnetic field, conspiring to lift weight against gravity. The quiet mechanism is diamagnetism, the universal but usually feeble tendency of electrons to rearrange their motion so that any applied magnetic field is locally opposed. And while every substance does this a few, pyrolytic graphite, bismuth, even water, do it strongly enough that with a well-shaped field you can see matter rise. To keep the picture honest, imagine the tiny loops traced by electrons in atoms and bonds. When you expose those loops to a field, they adjust in a way that creates a small counterfield, so the material prefers regions where the external field is weaker. And if you offer it a landscape with a sharp gradient, like the high spots and low spots around a pattern of permanent magnets, it will literally climb toward the softness, repelled from the stronger patches. That is why the simplest levitation kit uses 4 neodymium cubes arranged so their north and south poles alternate like a checkerboard. The pattern makes deep wells and ridges in the field near the surface, and a sheet of pyrolytic graphite, baked so its carbon layers lie in tidy stacks, finds a sweet spot where the upward magnetic push balances weight, while sideways nudges are corrected by restoring forces, a built-in stability that static magnets cannot give to ordinary magnetic materials. This stability skirts a famous no-go result about levitation because that theorem applies to materials that are attracted to stronger fields, while a diamagnet wants out of the strong regions, so a carefully shaped gradient acts like a magnetic hammock, supporting the object from below and recentering it when it wanders. In graphite, the effect is helped by anisotropy. The carbon planes are much more diamagnetic than the direction perpendicular to them, so a flat flake experiences a hefty repulsion when its broad face confronts the field, which is why the levitated tile prefers to sit level and why turning it on edge spoils the illusion. Bismuth, though less convenient, shows the same principle in bulk, and if you turn the dial of field strength high enough, even a droplet of water or a strawberry or a living creature will float because biological tissue is mostly water, and water is weakly diamagnetic. The iconic image of a small amphibian suspended in the bore of a powerful magnet is not a prank, but a vivid proof that diamagnetism is everywhere, simply too faint in daily life to notice. What you're seeing in all these cases is a tug-of-war between gravitational pull and magnetic pressure from the induced currents. And although you can write down formulas for the force, the intuition is simpler. A diamagnet treats strong field as a hill to avoid, so if the magnet pattern presents a low spot surrounded by rising terrain, the piece will sit in the low and drift back toward it after a bump. That makes the phenomenon useful beyond desk toys. Engineers exploit diamagnetic stabilization to calm otherwise unstable magnetic bearings, adding thin rings of graphite or bismuth to provide a passive restoring force that resists tilts and lateral slips without contact, which means less friction, little wear, and cleaner operation for delicate instruments. In research labs, diamagnetic levitation becomes a tool for precision. Free-floating droplets let scientists study fluid shapes, crystallization, and convection without containers that contaminate results, and the ability to adjust the effective buoyancy with field gradients creates a magnetic version of Archimedes' principle that can sort materials by their magnetic response or mimic microgravity conditions on a bench. At microscale, clever chemists have flipped the script by using paramagnetic salts to make the background slightly magnetic so that non-magnetic particles behave as if they were diamagnetic bubbles, levitating to heights that reveal their density or composition, a gentle, label-free way to separate cells or build structures one bead at a time. If you try this at home, the science is still honest. You'll need a wafer of pyrolytic graphite, which you can buy as a few paper-thin squares, and 4 or more strong neodymium magnets arranged in an alternating pattern. Place the graphite over the cross and it will rise and glide, and you can feel with a toothpick how a slight push leads to a soft, restoring slide rather than a crash. A tactile lesson in how gradients and signs, not just strengths, govern forces. What diamagnetism is not will also help you understand. It isn't sticky magnetism, and it isn't the dramatic flux expulsion of a superconductor, which is a different state entirely. Here, the material never becomes a perfect conductor. It simply resists the field enough that, in the right geometry, the repulsion beats weight locally. The effect has limits. You won't levitate a wrench with refrigerator magnets, because the force scales with both the material's inherent response and the square of the field. So desk demonstrations rely on strong rare earth magnets and very light, very diamagnetic samples, while the high-field levitations that hold water, grapes, or frogs use facilities that can produce tens of Teslas, with carefully shaped gradients and strict safety protocols. Those limits don't blunt the deeper point. Diamagnetic levitation shows you how much control lies in design rather than in brute strength. Shape the field landscape thoughtfully, and even a tiny universal response becomes a reliable support. A theme that recurs in sensors where diamagnetic rejection of fields helps isolate signals from noise, in balance scales that swap gravity for magnetic push to weigh minute samples, and in vibration isolation where levitated stages float above the rumble of the room. For your own thinking, the phenomenon offers a quiet metaphor. When a system refuses to be drawn into extremes, it will inhabit the modest middle you create, and small, reversible adjustments can hold it there gently. No clamps, just a landscape. That makes the safer choice the easier one. So the next time you see that graphite square perform its soft hover over a checkerboard of magnets, let the sight slow your mind and sharpen your curiosity. Electrons are not just charges. They are tiny artisans shaping the world's response to fields. A weak effect, repeated across a sheet of atoms and paired with a thoughtful pattern, can lift matter against the pull of Earth. And stability can come from saying no to intensity, from preferring the quiet valley to the bright hill, a lesson in physics and in patience, carried on a cushion of invisible lines. Superfluids. Fluids that climb walls. Set a cup on the table, dim the room in your mind, and picture a liquid so calm that when you pour it and walk away, it quietly climbs the walls, creeps over the rim in a paper-thin sheen, and drips down, the outside, as if gravity were only a suggestion. This is the signature of a superfluid, a state of matter where flow stops wasting energy and motion becomes a collective decision rather than a jostle of individuals. And understanding why it behaves this way begins with a simple shift in perspective. Below a special transition, the atoms stop acting like separate, colliding marbles and lock into a single coordinated wave that can thread through itself without the usual friction. In liquid helium-4, this change happens near a well-named point, the lambda transition around a couple of degrees above absolute zero, after which the liquid is most usefully described as two interpenetrating parts. One ordinary, normal component that still carries heat and rubs against walls, and one superfluid component that slips with essentially no internal viscosity, so thin films of the superfluid part spread along surfaces under the nudge of tiny forces, and with no internal resistance to bleed away their energy, continue to flow over edges and back down the outside in a slow, steady siphon you can collect in a second cup. That creeping film is not magic. It's the combination of attraction to surfaces, which pulls a microscopic layer of helium up the walls, and the zero viscosity channel inside that lets the layer keep moving. And because the superfluid part carries almost no entropy, bizarre, heat-driven effects appear. Warm one end of a superfluid through a fine filter, and a fountain emerges from the other end as the system tries to restore balance by sending the entropy-free component toward the warmth. A fountain effect that looks like a trick until you realize it is just the two components dividing labor, one moving heat, the other moving mass. Inside this world, rotation and turbulence obey rules you don't see in everyday fluids. Swirling motion breaks into perfectly discrete threads, quantized vortices, whose circulation comes in fixed packets set by nature's constants. So a spinning bucket of superfluid won't form a continuous whirlpool, but a lattice of identical twisters that you can sometimes image indirectly. Push the flow too hard, and even a superfluid will notice, because there is a critical speed beyond which the moving wave can shed excitations, ripples at low energy, and in helium-4, a peculiar family nicknamed rotons at higher energy. So, the dream of zero resistance has boundaries defined not by grit or dirt, but by the spectrum of allowed disturbances in the quantum liquid. Switch elements, and you meet other versions of the same idea with new accents. Helium-3, which is made of fermions rather than bosons, cannot pile into the same state directly. So at even lower temperatures, it forms delicate pairs that act collectively, leading to superfluid phases with internal structure rich enough to mimic features of high-energy physics in a tabletop jar. Entrapped, ultra-cold gases of alkali atoms, laser cooling and magnetic tricks let scientists create superfluids that expand like mist, yet flow without internal friction through narrow channels and around obstacles, giving a clean, adjustable stage where you can watch the birth of quantized vortices, tunnel weakly between two wells like a supercurrent, or send waves of temperature, second sound, rippling through the cloud because the superfluid and normal parts can slosh past one another. What makes all of this scientifically honest is how many cross-checks exist. Helium-4's heat capacity spikes sharply at the transition. Flow through impossibly thin capillaries stays large when any ordinary fluid would choke, a loop filled. With superfluid can carry current for months without fading. The spectrum of excitations inferred from scattering matches the speeds at which dissipation kicks in, and the response to rotation reveals those discrete vortex lines. Each observation, triangulating the same conclusion that this is a macroscopic quantum state, not a clever lubricant. The practical uses are not just curiosities etched into low-temperature textbooks. Gyroscopes that sense minute rotations by watching how a superfluid's vortices rearrange, detectors that translate tiny heat pulses into measurable flows, and refrigeration stages that rely on the superleak property to draw the entropy-carrying component away from the coldest chamber. But the deepest value is the way superfluidity rewrites your intuitions about liquids. It shows that viscosity is not an unavoidable tax, but an emergent behavior that can be engineered away when particles agree to move as one, that heat can travel as a wave rather than a diffusive smear, and that rotation can fracture into tidy threads rather than a continuous swirl. If you crave a mental model with no equations, let it be this. In an ordinary liquid, each atom is on its own, bumping, slowing, and scattering, so every step leaves a little energy behind as heat. In a superfluid, the atoms have agreed on a shared choreography, so the motion cannot easily degrade into random jiggles. Only specific disturbances with specific costs are allowed. And as long as you steer under those limits, the flow remains exact and unfrayed. There are edges to respect. Contact with rough walls can create a tangle of vortices, small impurities can pin motion, and the superfluid fraction shrinks as temperature rises until the magic evaporates back into ordinary swirl. But within those edges, the behavior is robust enough to build instruments and subtle enough to test fundamental ideas about order, symmetry, and collective motion. carry the human echo gently. There are moments in your life when effort feels like stirring honey, every push warmed into loss. And there are rarer moments when a group's attention locks and motion becomes almost effortless, carrying you farther than the input should allow. Superfluidity is the physical proof that the second mode exists, that under the right conditions friction can fall away, not by brute force, but by coherence. So when you picture a fluid climbing a wall, let it be both a precise phenomenon, from vanishing viscosity and quantized vortices to two fluid flow and temperature waves, and a soft reminder that sometimes the path to less resistance is not more pressure on the same old channels, but a careful change in how the parts agree to move, a quiet choreography that turns spill into stream, drag into glide, and a cold, thin film into a lesson about how order can carry you up and over the rim. Granular physics, sand that behaves like a fluid. Tip a bucket of dry sand and you'll watch a contradiction pour out. It streams like water, piles like a tiny mountain, then suddenly freezes into a shape that holds its slope as if it were a solid sculpture. The everyday riddle that granular physics turns into a set of rules about how many particle materials behave when each grain is big enough to ignore heat and small enough to act collectively. The first move toward clarity is to admit that sand is neither a normal liquid nor a normal solid, because it lacks the gentle thermal jostling that lets molecules self-heal, and it loses energy every time grains rub or collide. So history matters. The path you took to make the pile lives on in its interior, and boundaries matter too, because friction at walls and between grains creates force chains, jagged filaments of stress that carry most of the load in patterns you can literally visualize with photoelastic discs. Push gently, and only a few chains light up. Push harder, and a branching network snaps into place. And if a chain breaks, the material can suddenly slump or avalanche without any change in the average tilt. That's why a heap sits at a well-defined angle of repose. The slope stores stress along specific lines until a patch fails and cascades down. Then the surface heals to roughly the same angle again, a classic example of how local friction sets global behavior. Funnel the same grains through a silo and a different quirk appears, arching, which is the way grains above an orifice spontaneously build a self-supporting vault that chokes the flow. So discharge isn't smooth like water, but a rhythm of runs and stalls whose statistics depend sensitively on hole size and grain shape. And every engineer who moves powders learns to respect this by choosing hopper geometries that favor mass flow over funnel flow, smoothing corners, or adding gentle vibration to break arches before they become blockages. Flow itself splits into regimes. In the slow limit, motion is quasi-static and resisted by a yield stress. You must push beyond a threshold before anything moves. While faster shear creates a grain gas, where random jiggling motion emerges from inelastic collisions and acts like a kind of temperature that has nothing to do with hot or cold, and everything to do with how violently grains buffet one another. In between lies a dense inertial regime where simple liquid formulas fail and the resistance to flow depends on how quickly you shear compared with how fast grains can rearrange. A ratio that sets whether the material behaves more like a creeping soil or a roaring slide. And one of the striking signatures of this middle ground is dilatancy, the counterintuitive tendency of a packed bed to swell when sheared because grains need extra room to roll past neighbors, a fact you can feel by stepping on wet sand. Push sideways and water rushes to fill the opening, leaving your footprint briefly dry as the grains unlock. Add vibrations, and yet another face appears. Tapping compacts a loose pack over many cycles as grains discover tighter arrangements, but stronger shaking can unjam a settled pile and send it flowing again, which is why the same shoebox of rice alternately densifies and loosens depending on how hard you carry it, and why industrial hoppers use just enough agitation to prevent arches without turning stored product into dust. Mix two sizes together, and nature teases you with segregation rather than blending, the famous Brazil nut effect, where larger grains climb to the top under shaking, because small grains percolate down between gaps while convection cells carry the big ones upward, although by changing density or shaking conditions, you can flip the outcome and send heavy intruders to the bottom. A reminder that granular systems have multiple competing routes to order, and that getting the mix you want means tuning the path, not just the ingredients. At field scale, the same rules write themselves across landscapes. Sand dunes migrate as wind drives grains up the gentle face, and avalanches reset the steep slip face. Ripples on beaches record a tug-of-war between flow and gravity at grain scale. Debris flows and dry avalanches owe their power to grains losing and regaining contact. And even earthquake faults are mediated by a thin layer of crushed rock whose grains lock, dilate, heat surrounding water, and sometimes liquefy. The interface when shaking pumps pour pressure. Physics on the same stage as your desktop sandpile, only louder. In devices and factories, getting granular physics right saves money and headaches. Pharmaceutical powders must not segregate before tableting. Catalysts in packed beds must not channel and starve parts of a reactor. 3D printing powders must spread without clumping, and grain silos must be designed to avoid uneven stresses that can buckle walls, because the weight above doesn't simply add up, but redistributes through those mischievous chains. A phenomenon that even produces the Janssen effect, where added depth increases pressure only weakly after the walls begin carrying load. Add a little liquid and cohesion steps in through microscopic bridges between grains, turning free-flowing beads into a sticky sandcastle mixture that supports arches stronger than dry ones, yet fails catastrophically when the bridges snap. Another illustration that tiny interactions at contacts decide the fate of the whole. If all this seems messy, the progress comes from asking the right kind of questions with the right kind of experiments. Tabletop channels and rotating drums let you map when flow starts and stops. X-ray imaging and refractive index matched fluids expose motion inside opaque packs. Acoustic probes listen for the telltale crackle of rearrangements, and numerical models that track every grain now connect contact laws to bulk behavior well enough to guide design. There are clean, teachable relationships hiding in the clutter too. The discharge rate from a wide silo hardly depends on how much is left above, but instead on the orifice size and grain properties. Chute flows stabilize when the layer finds a thickness that balances gravity and internal friction, and shear bands, narrow zones where most deformation concentrates, form predictably near walls or stress concentrators, allowing tools to channel failure away from where it would do harm. Even at the whimsical edge, granular physics is honest and useful. Granular jets shoot upward when a falling ball pushes grains aside, and they refill with speed, offering simple tests of how momentum and dissipation share the bill, while low-gravity experiments on parabolic flights and space stations explore how regolith on asteroids sticks, flows, and resists. Knowledge that now shapes how explorers touch and sample worlds, where the surface is a thin skin of grains balanced between cohesion and drift. What should you carry away? That a heap of sand is a society of particles whose rules come from contact, friction, and geometry, rather than from molecular forces. That many of its surprises, angles that hold, avalanches that reset, flows that choke, mixtures that self-sort, are not noise but signatures of a world where energy is always leaking away and rearrangements cost effort, and that the smartest way to control such systems is to design the journey as carefully as the destination, because the final pattern depends on how you poured, shook, tilted, or tapped. There is a quiet human echo in this too. When interactions are rough and information dissipates quickly, history and boundaries loom large, bottlenecks and arches can stall progress, and small, well-placed perturbations, an extra exit, a gentler slope, a timed tap, can unjam a stuck flow far more effectively than brute force. Granular physics teaches you to see the hidden structure in mess and to respect the fact that in a world of finite friction, order is not a default, it is an achievement, one that you can coax, measure, and trust once you learn where the force chains run and how to keep them from snapping at the wrong time. Non-Newtonian fluids, oobleck and the secret of shear. Wrap your knuckles on a shallow tray of milky cornstarch slurry and it punches back like rubber. Then rest your hand lightly and it welcomes your fingers as if nothing had changed. This small, mischievous experiment opens the door to non-Newtonian fluids, substances whose resistance to flow is not a fixed personality, but a mood that shifts with how you disturb them. And the lesson is both practical and quietly radical. The way you push matters as much as how hard you push, because the microstructure inside these materials, polymers, particles, droplets, rearranges on the fly to meet your demand. Start with the celebrity, oobleck, a humble mix of cornstarch and water that stiffens when you stir fast or strike it, a behavior called shear thickening, yet flows when you move slowly. And the simplest honest picture is this. At gentle rates, thin layers of water keep the starch grains sliding past each other. But as your motion speeds up, the liquid films that separate neighboring grains are squeezed out faster than the water can refill. So grains touch directly, and in that squeeze, build a temporary skeletal network that bears load. It's not the permanent framework of a solid. It's a stress-borne scaffolding that appears under impact and dissolves when the stress relents, which is why a quick punch lets you walk on a pool of oobleck while lingering weight sinks. Confinement makes this even more dramatic. Push hard and the mixture tries to expand sideways, a counterintuitive, normal pressure. But if the container walls resist, the particles press more tightly into their fleeting contacts, and the material hardens further, a feedback that explains why the same recipe can feel like armor under a slap and like soup under a spoon. Flip to the opposite personality, and you meet shear thinning, ketchup that refuses the bottle until you shake, paint that spreads under the brush and then stops sagging, blood whose flow eases through narrow vessels when the velocity rises. Here, the microstructure is different, often long molecules or soft aggregates that, when left alone, coil and tangle into a mess that resists motion. But under shear, they align and streamline, lowering the resistance just when you need it. A self-organizing kindness that makes everyday tasks possible. Add time to the story and things grow richer. Some fluids are thixotropic, meaning they thin under sustained shearing and only slowly rebuild their internal scaffolds when left at rest. Think yogurt that loosens when stirred and firms again, in the fridge, while a rarer class is rheopectic, stiffening gradually with continued agitation. There is also elasticity hiding in many liquids, especially polymer solutions and melts. They remember being stretched for a while, so they climb a spinning rod, swell as they leave a nozzle, or snap back when flow stops. Behaviors that look like magic until you realize that long chains take time to uncoil and recoil, and if your forcing matches their memory time, you wake effects that a simple viscous liquid cannot show. To describe all of this without equations, carry two clocks in your head. One is set by what you do from the outside, how fast you shear, how abruptly you strike. The other is the material's internal relaxation time, how quickly its microstructure can rearrange. And when your clock is slower, the fluid has time to adapt smoothly and acts tame. But when your clock runs faster, the material is caught off guard and reveals hidden stiffness, alignment, or resistance. With oobleck, that mismatch creates the familiar instant solid under impact. With polymer solutions, it unlocks elastic recoil and rod climbing. With surfactant micelles, tiny self-assembled tubes and worms, it can trigger sudden thinning because the little structures break and line up under stress. This dependence on history and rate is why the same bucket of stuff can jet, rope, buckle, or refuse to budge depending on how you handle it, and why, in the lab, we plot stress against deformation rate and sweep up and down to see whether the curve follows the same path or remembers where it has been. Beyond kitchen theatre, the stakes are large and real. Drilling muds are engineered to be thick at rest, so they hold cuttings in suspension, then thin when pumped, so they travel easily. 3D printing inks are tuned to flow through a nozzle, yet keep their shape once laid down. Body armor fabrics are impregnated with shear thickening colloids, so a soft vest stiffens exactly when struck. Food textures, from custards to sauces, balance mouthfeel against stability by blending ingredients that lend shear thinning for spread and elasticity for structure. Even inside you, synovial fluid in your joints and the blood in your vessels rely on non-Newtonian character to reduce wear and deliver oxygen efficiently in a world where vessels narrow and widen with every heartbeat. To make the picture concrete, imagine peering into a sample under a microscope while you shear it. In a shear, thinning fluid, long chains stretch and line up with your motion like people turning sideways in a crowd. In a shear, thickening suspension, increasing strain rate forces particles into frequent contact where the lubricant fails, and clusters of neighbors lock briefly into load-bearing clumps. In viscoelastic liquids, small tracer beads feel a tug. That depends not only on where they are, but on how recently the surrounding chains were stretched, so their paths betray memory. And in concentrated emulsions, droplets packed so tightly that interfaces touch, flow localizes into narrow bands, while the rest holds, a kind of traffic lane that appears spontaneously because the system cannot deform uniformly without tearing interfaces. If you want to sort the zoo without jargon, 5 families cover most of what you'll meet. 1. Rate-thinning aligners, ketchup, paint, blood, that get smoother the faster you move them. 2. Impact-hardening suspensions, oobleck, some protective, slurries that jam under sudden stress. 3. Viscoelastic memorists, polymer solutions, silly putty, that bounce back or climb rods because stretched chains act like tiny springs. 4. Yield stress pastes, toothpaste frosting, that act like solids until a threshold is exceeded, then flow. 5. Time-dependent rebuilders or drillers, thixotropic gels, and the rarer rheopectic mixes, whose response drifts with sustained forcing. Lurking across all of them is geometry, particle size and shape, droplet packing, chain length, and especially boundaries and confinement decide how easy it is for the internal structure to rearrange. So the same material in a narrow gap may appear stubborn while in a wide vessel it yields gracefully. The honest limits matter too. Cornstarch pools that support running feet will swallow a lingering visitor because the contact network is temporary. Protective fluids that stiffen on impact still need breathable fabrics and thoughtful design because repeated hits or temperature changes can erode their behavior. And measurements of these materials demand patience, since starting and stopping flows can imprint memories that confuse quick tests. Experts wait for steady states, reverse, directions to check for history, and use multiple recipes of deformation to separate elastic, viscous, and time-dependent parts. Yet once you learn to read the signs, you can turn unruly matter into instruments and tools. Dampers that hush vibrations by converting sudden jolts into internal rearrangements. Pipetting protocols that avoid bubbles by matching speed to relaxation. Times conveyor systems that prevent segregation by choosing the right shaking profile. Even outreach demos that honestly teach how complexity is not caprice, but structure responding to how you ask. And there is a soft human lesson flowing here as well. In a Newtonian world, we pretend effort scales neatly with push, but in many lives, as in many fluids, strain begets change. Go gently and the path clears. Press suddenly, and resistance rises. Persist thoughtfully, and a threshold yields. Oobleck is not just a party trick, it is an invitation to notice how context writes behavior, how microscopic arrangements respond to macroscopic demands, and how designing the rate, not just the force, can turn mess into use. So the next time a sauce refuses the bottle or a slurry turns solid under your palm, let curiosity slow you down. Ask what structures are aligning, what contacts are forming, what memories are being written, and consider how, by changing tempo, you might coax the material and maybe your own habits into a state that flows. Acoustic levitation, trapping objects with sound. You felt bass thrum in your chest and watched a loudspeaker ruffle air, but imagine shaping that invisible push so precisely that a bead or droplet hangs mid-air in a quiet pocket, held not by strings or magnets, but by the steady shove of sound. Acoustic levitation takes this intuition that sound carries momentum and exerts pressure, and turns it into a controllable tool, building standing waves that carve tiny wells and ridges in the air's pressure landscape, so that small objects settle into the wells and stay put, allowing you to handle matter without touching it, to heat, cool, mix, or watch it transform free of any container's contamination. The simplest trap uses ultrasound, pitches above your hearing, because high frequencies make short wavelengths and therefore tightly spaced nodes where the pressure oscillations cancel. Mount a piezoelectric transducer opposite a hard reflector. Tune the spacing to an integer multiple of half a wavelength, and the air in between organizes into a stack of invisible layers, each with a pressure node where the oscillation amplitude is minimal, and the time-averaged radiation force points upward strongly enough to balance gravity on a millimeter-scale object. Most solids and droplets in air prefer those nodes, so if you introduce a tiny sphere with tweezers and let go near one, it shifts until the acoustic forces cancel its weight, and lateral gradients herd it to the center line like a marble finding. The bottom of a bowl you cannot see. Under the hood, nothing mystical is needed. As sound waves compress and rarefy the air, they transfer a little net momentum to anything they strike. And when waves bounce back and forth between transducer and reflector, their interference builds steady regions where that push doesn't just average to zero, but creates a stable force pattern. For a small sphere, the net effect can be summarized as an acoustic potential whose valleys lie at the nodes, and the curvature of those valleys sets how stiff the trap feels. Raise the sound intensity, and the bead vibrates faster around. Its resting point, lower it, and the trap softens, just as a stiffer spring tightens a mechanical oscillator. Because it's the pressure field that does the lifting, you don't need the object to be magnetic or electrically charged, and you don't even need it to be especially light. What matters is the balance between gravity and the acoustic radiation, pressure you can safely generate in air. At the tens of kilohertz commonly used, arrays of coin-sized transducers create pressure amplitudes large enough to hold plastic beads, seeds, bits of foam, or microlighter droplets with ease, and by shaping the interference pattern dynamically, you can move the trap in 3 dimensions, carrying the payload along like a tiny conveyor in open space. This is where phased arrays become the stars. By driving dozens or hundreds of ultrasonic emitters with controllable phases, engineers draw pressure landscapes on demand. Single traps that translate smoothly, stacks of traps that pass objects, hand-to-hand loops and spirals that ferry droplets through mixing sequences, even shapes that act like acoustic lenses to focus or split beams, turning levitation into acoustic manipulation, a contactless factory line for things too fragile or too reactive to touch. You'll sometimes hear about tractor beams, and there's a sober truth behind the headline. If you set up a field where gradients of acoustic intensity pull an object toward a region of lower energy, the object will climb that gradient and follow the trap, so a phased array can indeed draw a bead toward the source, or push it away without mechanical parts, not by violating physics, but by moving the valley in which the bead naturally sits. With clever patterns, you can even spin objects, create torque, and orient asymmetric particles to present specific faces to a beam or a camera. The workhorses in laboratories are droplets and powders, because they tell rich stories when freed from walls. A levitated droplet can be heated with a laser to watch evaporation and internal convection without a container that seeds crystals or cools unevenly. Reactive liquids can be mixed mid-air to capture transient products before they stick to glass. Pharmaceutical particles can be floated to measure how they absorb moisture or release active compounds without compaction. And sticky melts that crust on container walls can be studied in their pure form to understand how alloys solidify. Industry has grabbed the idea at smaller scales too. Inside microfluidic chips, surface acoustic waves launched along a piezoelectric substrate leak into the liquid above, creating standing patterns that nudge cells and droplets sideways into different channels. Acoustic tweezers, that sort, concentrate or merge samples gently, useful when electric fields would tear membranes or magnetic tags would complicate chemistry. You may wonder how something as soft as air can hold against gravity, and the honest answer is that it relies on intensity and gradients, not brute density. At the pressures used, the instantaneous sound field is loud by any everyday standard, ultrasound levels that would be painfully intense if audible. But the energy is deposited and withdrawn cyclically, and when arranged carefully, it produces a steady upward force while keeping heating and streaming under control. Safety is managed by working at frequencies humans can't hear, and by enclosing arrays, so stray reflections don't fog the room with ultrasound, and by choosing payloads that don't absorb too much acoustic energy and overheat. Stability is the other honest constraint. A bead held in a single standing wave is stable along the beam axis, but can be sloshed sideways if the field isn't well formed. So practical devices use shaped reflectors, feedback from cameras, or multi-axis arrays that create three-dimensional cages, acoustic bottles with walls on every side, to keep the objects centered even when air currents or small shocks arrive. In liquids, where sound travels faster and attenuates differently, similar ideas work at smaller scales, letting you corral cells or bacteria at nodal planes without poking them with glass needles. The physics deepens with neighbors. 2. Levitated. Droplets don't simply ignore each other. The oscillating pressure field around each creates attractive or repulsive secondary forces that make them orbit or lock at set distances. And this can be either a feature for arranging particles into patterns or making controlled collisions, or a bug when you want one drop at a time. So designers adjust frequencies, phases, or trap spacing to keep interactions in the desired regime. In the same vein, a trapped object can leak momentum to the air and set up steady microflows called acoustic streaming, which will swirl impurities around and can gently erode a soft payload. A reminder that every levitation scheme has hydrodynamics attached and must be tuned with the full environment in mind. To separate the methods, it helps to know there's also a near-field cousin, where a vibrating plate creates a thin squeeze film of oscillating air that can support heavier, flat objects a hair's breadth above the surface, useful for frictionless bearings and delicate handling. But this version is not the free space hover people picture. The classic, non-contact levitation for droplets and beads uses standing waves in open air or an open cavity, giving you a perch in the middle of nowhere. Despite the romance of floating things, the most powerful contribution of acoustic levitation is measurement without touch. When there's no container, you eliminate nucleation sites and impurities from walls. You avoid mechanical stress that cracks crystals, and you remove the tiny heat leaks that confuse thermal data, so the numbers you read, evaporation rates, reaction kinetics, melting curves, represent the material itself rather than the material plus the vial. That's why aerospace and energy labs have used levitated samples to test how fuels atomize and burn, how molten droplets solidify into precise microspheres, and how exotic alloys cool without stirring from a container, turning levitation into a metrology tool as much as a spectacle. There are, of course, edges you can't cross today. Large, dense objects need force levels that would roast or deafen under ordinary conditions. Very delicate biological payloads can suffer from shear. If streaming isn't tamed, and the traps have finite depth, meaning a big gust or a misstep can knock a sample out, yet the trajectory is forward. Cheaper phased arrays controlled by off-the-shelf electronics, better models that predict stable trap shapes for complex objects, and integrated systems that pair levitation with cameras, spectrometers, and microheaters. So you can not only hold a sample, but interrogate it fully while it floats. If you carry one picture away, let it be this. By drawing a map in pressure rather than in matter, you persuade objects to occupy places you choose. And because the map is programmable, phases and amplitudes set by software, you gain a quiet kind of dexterity over the small world, one that tidies stubborn powders, nurses droplets through reactions, and centers fragile cells without a hand ever touching them. It's a reminder that control often comes not from grabbing harder, but from shaping the field they live in. The same lesson you hear elsewhere in physics, so that when you turn down the lights and a bead lifts into the hush between a speaker and a reflector, you are watching more than a trick. You are watching a design principle made visible, the art of trapping with nothing but rhythm, and the promise that gentleness, applied with structure, can hold and move the world. Light-sculpted matter. Optical tweezers at work. Take a laser beam, squeeze it through a high-quality microscope lens until it narrows to a brilliant pinprick, and then watch a micrometer-size bead drift against the random buffeting of water and settle into that glow as if a hand had pinched it from afar. This is the first honest glimpse of light sculpting matter, the quiet power behind optical tweezers. What happens is wonderfully concrete. In a tightly focused beam, the intensity rises steeply toward the center, and a transparent particle with a higher refractive index than its surroundings feels a pull up that brightness hill, because light refracts within it and redirects momentum toward the focus, producing a restoring force that drags the bead back whenever it strays, while a competing push from photons scattering forward is tamed by focusing strongly so the gradient wins. Use near-infrared colors to minimize absorption and heating. Choose water or a gentle buffer, and that pinched point becomes a spring you can turn with light alone, strong enough to balance gravity on small objects and precise enough to measure displacements far below what your eye can see. Calibrating that spring is part of the craft. Watch the trapped bead jitter from thermal motion and infer the stiffness from its power spectrum, or drag the surrounding fluid past it at a known speed and read the force from the tiny offset. And once you've done that, the trap becomes not only fingers, but a scale, able to weigh forces in the piconewton range where biology's machinery lives. With that capability in hand, researchers learn to grab a single molecule by its ends, DNA, RNA, or a protein tethered to microscopic handles, and stretch it gently to map out its elasticity, to watch it unzip and rezip base pairs one after another, or to time the stepping of molecular motors that haul cargo inside cells. Kinesin's regular strides show up as nanometer-scale hops against the trap's restoring force. The enzyme that copies DNA slows and stalls under a controlled load dial with laser power, and misfolded proteins reveal hidden intermediates as you tug and release in cycles, converting the abstract idea of an energy landscape into a literal curve measured one pull at a time. The beauty of tweezers is their neutrality, because the force comes from light's momentum. You don't need your target to be magnetic or charged, and you can work inside salty, living solutions where electrodes and magnets would disturb chemistry. At the same time, neutrality doesn't mean passivity, so good practice matters, keeping powers modest, wavelengths kind to cells, and exposures brief, because high intensities heat and bright dyes can absorb, and the point of the tool is to probe without scarring. Once a single trap feels familiar, software makes dozens. Take a spatial light modulator, essentially a programmable phase mask, and imprint patterns that split one beam into many, each focus a separate pair of fingers. That can sort cells. Assemble colloidal crystals one bead at a time, or hold a dozen droplets while a camera watches them react. Add holography, and you can braid traps in 3 dimensions, draw conveyor belts for particles, create optical spanners that rotate birefringent objects with circularly polarized light, and even spin tiny rotors to measure torque on molecular machines. Tilt the focus into a microfluidic channel, and you can build contactless valves and pumps from light alone, catching a bead and dragging it upstream to block flow, or corralling cells into lanes without touching their membranes. The same principle extends beyond water and life. In air or vacuum, a trapped nanoparticle becomes a pendulum that moves in response to feeble forces, gravity's tiniest gradients, whispers from surface charges, the faintest gas flows. And, by cooling its motion with feedback, you can study the borderland between classical vibrations and quantum quiet. A developing field where levitated optomechanics uses the trap's own light to sense and damp motion until the particle nearly stops wiggling at all. In soft matter and materials, optical tweezers double as microreology probes, measuring viscosity and elasticity inside crowded gels and cytoplasm, by watching how a trapped probe bead relaxes after tiny nudges. A local map of mechanical properties, drawn without dyes or stains. In microassembly, beams herd colloids into lattices, knit them into photonic structures, or position catalysts precisely on a chip where chemical growth will take over later, turning light into a construction crew that never leaves fingerprints. None of this requires mysticism, only careful accounting of momentum and refractive landscapes. Each ray bends in a particle, the particle returns the favor by feeling a force in the opposite direction, and a lens that pushes light into a steep enough gradient turns that balance into a stable trap. Still, the limits are real and instructive. Absorbing particles feel photophoretic pushes that can slip them from your grasp. Irregular shapes add torques you must either exploit or counter, and non-spherical cells can align in ways that complicate naive force readings. So tweezers work best when paired with honest diagnostics. Imaging to watch orientation, spectra to check heating, controls where you vary beam power and verify that the force scales as a spring would. When a measurement must be gentler still, you can shift tactics, using lower powers and averaging longer, or switching to dual beam traps that cancel net scattering, or embedding the target in a droplet to share heat, because the tool is versatile, enough to be tuned for barely touch as well as firm hold. A lesser-known strength is how optical tweezers teach cause and effect in messy systems. Build two traps and tug microscopic gears, DNA origami wheels, protein lattices, and you learn where stiffness lives. Sprinkle tracers and record there. Confine jiggles, and you learn how crowded interiors impede diffusion. Couple a trap to a feedback loop, and you can create virtual potentials, landscapes that don't exist in matter, but do exist in math. Corralling a bead into wells or ratchets, whose shapes you design on a screen, to test how systems extract work from fluctuations, or how molecular motors might bias random motion into useful steps. Even quicker payoffs flow to clinics and labs. Trap a bacterium and apply calibrated nibbles to test cell wall strength as an antibiotic acts. Hold a red blood cell and measure how its membrane stiffens in certain diseases. Arrange a line of droplets and merge them pairwise with pulses for high-throughput chemistry, where wall effects once dominated. And because everything happens under a microscope, you always have the comfort of seeing what your forces are doing rather than inferring blindly. It's worth pausing on the historical hinge. Decades ago, Arthur Ashkin and colleagues realized that focusing light could first push, then trap, and they turned a curiosity into a craft that now reaches from single-molecule biophysics to precision metrology. The secret of that longevity is that optical tweezers scale. The same equations govern a 10-micrometer bead and a 100-nanometer vesicle, a single trap and a holographic field of many, a gentle probe in a living cell and a stiff spring in a polymer melt. What changes is how you set the knobs: wavelength, numerical aperture, power, feedback, and how honestly you calibrate. If there's a human lesson folded into the physics, it is that shaping the field reshapes what's possible. By drawing a steep valley in brightness, you create a place where order holds, where a random bead becomes a reporter of forces, where a fragile strand becomes an instrument string you can pluck and listen to. And when you've finished and the light fades, the bead swims off, the cell continues on, and the only trace is the knowledge you pulled from a system that would not have yielded it to a rougher hand. A reminder that precision is a kind of kindness, that the softest grip can teach the most, and that even a beam you cannot feel can become a tool for asking matter to reveal how it works. Quantum annealing, landscapes of solutions, frozen in chips. Imagine taking a messy, real-world decision: how to route trucks, staff a hospital night shift, place antennas on rooftops, or select a basket of investments under tangled risks, and pouring it onto an abstract landscape of hills and valleys, then cooling that landscape until a tiny explorer tries to settle in the lowest valley it can find. Quantum annealing turns that picture into hardware by carving your problem into the energy of a network of interacting spins on a cryogenic chip, then guiding the network from an easy, wavy terrain to the rugged terrain that encodes your costs and constraints, hoping that quantum tunneling helps the explorer slip through thin mountain walls instead of climbing over them. In plain terms, you rewrite your objective as a quadratic, unconstrained binary optimization, QUBO, or an equivalent Ising model. Variables become binary spins, pairwise penalties become couplings, hard constraints become large energy costs, and the machine starts these spins in a superposed, flexible state set by a strong transverse field, a kind of gentle agitation that lets them explore, and then slowly turns that agitation down while turning your problem's couplings up, so that, if the change is slow enough and noise is kind enough, the collective state tracks the bottom of the evolving landscape and ends near a good, ideally optimal, solution. This procedure is called an anneal by analogy to metallurgists cooling molten alloys, so defects heal. And the quantum part is that, during the early and middle stages, the chip encourages coordinated flips of many spins at once by tunneling through narrow barriers that would stall a classical random walk, a move that can be particularly helpful when your cost function is full of tall, thin obstacles between many nearly good regions. The chips that perform this trick are tangible and specific. At their heart sit thousands of superconducting loops interrupted by Josephson junctions, devices that behave like controllable, low-noise quantum spins when chilled to tens of millikelvin in a dilution refrigerator. Each loop can prefer one of two circulating currents, your 0 and 1, and adjustable couplers set where the pairs prefer to agree or disagree, thus encoding the quadratic terms of your cost. Control lines sculpt the anneal schedule, the time, course by which the easy landscape fades and your problem's landscape takes over. And modern machines let you decorate that schedule with pauses, quenches, and even reverse sweeps so you can, for example, pause near a delicate point where the two lowest valleys almost meet, an avoided crossing, to give tunneling more time to do its work. Or reverse anneal from a guess you already have to see if a small quantum nudge can escape its local trap. Because on-chip connectivity is never all-to-all, architectures like Chimera and Pegasus offer a woven grid of neighborhood links rather than arbitrary pairs. Dense real problems must be embedded, which means representing one logical variable as a chain of physical spins tied strongly together so they act as one. A step that adds overhead. Chains can break if you tie them too loosely and freeze too early if you tie them too tightly. So picking the right chain strength is part science, part craft. And success often improves when you randomize gauges, flip signs consistently across variables, and average results to cancel small, stubborn biases. None of this guarantees a miracle. The device lives at a small but non-zero temperature, so thermal kicks compete with tunneling, noise and calibration drift smear the landscape, and the evolution cannot be infinitely slow because external disturbances and practical time budgets intrude. So there is a freeze-out point beyond which the state largely stops adapting. Good. Schedules push that point later, poor ones lock in too soon. For some classes of problems, classical heuristics such as simulated annealing, parallel tempering, or carefully tuned local search climb just as well or better, and so you use the quantum chip as one tool in a hybrid loop. Classical code cleans. The data builds the embedding, prunes obvious dead ends, and polishes solutions afterward, while the quantum pass supplies a global shake that can vault across the thin barriers that trap purely local moves. This division of labor explains many reported wins. The advantage, when it shows, tends to appear in landscapes with many near-degenerate minima separated by skinny walls, where coherent multi-bit tunneling helps, rather than in broad, gently rolling basins, where classical wanderers meander efficiently anyway. To make it concrete, imagine you're solving a max cut on a big, irregular graph. Split the nodes into two groups to cut as many edges as possible. You translate each edge into a coupling that prefers its endpoints to disagree. Decorate the graph with penalty couplers for any side constraints. Chain logical nodes across the hardware fabric until the problem fits, and then run many anneals while twiddling schedule parameters, chain strengths, and gauges. You inspect outputs, bit strings, with identical energies to spot degeneracy you can exploit. You let a classical local search clean single-bit flubs, and you rerun batches with a short mid-anneal pause when you suspect the relevant crossing sites at a certain fraction of the schedule. Similarly, with workforce scheduling, you encode shifts and rest rules as penalties, so any assignment that violates a constraint pays a steep energy price and falls out of contention. While with portfolio timing, you trade off return and risk by giving risk a tunable weight in the energy. Dialing that weight traces a frontier of optimal trade-offs as the annular samples low valleys along the curve. None of these mappings require mysticism, only careful bookkeeping, and they reward patience because small changes in penalties can flip the dominance of valleys and turn a poor sampler into an effective one. It's also useful to understand what quantum annealing is not. It is not a universal gate model quantum computer that can run arbitrary algorithms with error correction, and claims of blanket quantum speedup must be tested case by case against the best classical solvers on well-chosen benchmarks. What it is today is a specialized optimizer that implements a physical version of adiabatic guidance plus tunneling under realistic noise. A machine that you program by shaping energies rather than writing instruction lists. And one that thrives when you respect its strengths: sparse but improving connectivity, fast repetition rates, rich schedule control, and mitigate its limits, embedding overhead, analog drift, finite temperature. The research frontier is alive with ideas, designing non-uniform schedules that adapt to each problem's bottlenecks, using reverse annealing to refine good guesses from classical heuristics, coupling small clusters more strongly to encourage collective tunneling events, and exploring error suppression tricks that flatten spurious bumps in the hardware landscape so the intended problem shines through. Equally important are interpretability practices, reporting not just best found energies, but full distributions of outcomes, including gauge averages and chain break statistics, so you learn whether the device is returning the same value reliably, or exploring many shallow neighbors that a classical post-processor can stitch into something better. If you carry a deeper lesson from all this, let it be that solving hard problems is often about shaping dynamics, not beating them into submission. Rather than brute forcing every possibility, you design a landscape where the right answers are easy to reach and the wrong ones are costly. You cool slowly where it matters and quickly where it doesn't. You accept that noise is part of the world and build procedures, gauges, pauses, majority votes that average it away, and you let your solver, quantum or classical, do what it does best in a coordinated loop. And perhaps there's a human echo worth keeping. When your own projects sprawl into rugged terrains of competing priorities, sometimes the move that changes everything is not more effort up the same steep slope, but a new path that cuts a tunnel under it, reframing constraints as design, pacing your schedule through bottlenecks with patience, and allowing a little randomness to jostle you out of comfortable but inferior valleys. That is the quiet promise of quantum annealing as it stands today. Landscapes of solutions, frozen in chips yet malleable under thoughtful hands, teaching you that with the right mapping, the right schedule, and the right mix of tools, even tangled problems can settle into shapes you can use. Weak measurements. Reading the Almost-Unmeasurable. Suppose you wanted to learn the direction a whisper is moving without interrupting the conversation. No grabbing the speaker, no shoving a microphone in their face, just a brush of air against your cheek that tells you something while leaving the words intact. That is the spirit of weak measurement, a way of reading a quantum system so gently that a single glance barely says anything, but also barely disturbs, and by repeating the glance across many identical preparations, and, crucially, keeping only those runs that end the way you ask, you average your faint clues into a surprisingly sharp picture of what was happening between prepare and detect without shattering the very behavior you want to study. In practice, the recipe is concrete and not mystical. You start with a system prepared in a known initial state. You couple it to a meter so softly that the meter's pointer barely shifts. Think of a tiny prism that nudges a beam left or right, depending on polarization, or a microwave resonator whose tone shifts by a hair depending on a qubit's orientation. You then post-select only those trials where a final check finds the system in a specific state you choose, and you average. The minuscule pointer wiggles from those accepted trials. The average you extract is called a weak value, and it can be odd in ways that make headlines, sometimes appearing to lie beyond the range of the property's usual eigenvalues, sometimes even flipping sign. Yet the strangeness is a faithful report of interference between the pre- and post-selected states, not a claim that the system literally possessed an impossible value in a single run. The power of this approach shows up first in optics, because light is easy to prepare, nudge, and detect. Take a laser beam with nearly horizontal polarization, let it graze a thin birefringent crystal that displaces the vertical and horizontal components by the tiniest amount, too small to see directly. Then set a second polarizer, almost, but not quite, orthogonal to the first, so that only a small fraction of the light gets through. On those rare passes that survive, the tiny displacement is multiplied into a measurable beam shift, and by scanning how that shift changes while you tweak the alignments, you can read effects as small as nanoradian tilts, picometer deflections, or the subtle spin-hall drift that polarization imprints on a beam's path. Measurements that would drown in technical noise if you tried to read them head-on. The same principle travels beyond light. In solid-state physics, a quantum point contact weakly senses whether an electron sits on a nearby island without fully collapsing it, letting researchers watch charge hop in real time. In superconducting circuits, a dispersive readout tone taps a qubit so lightly that a single shot is nearly useless, but continuous weak monitoring lets you reconstruct the qubit's quantum trajectory, a meandering probabilistic path between states, by filtering the noisy stream. And with fast feedback, you can even stabilize delicate oscillations or catch an incipient quantum jump and nudge the system back before the transition completes. These achievements are not the same as the non-demolition measurements you might have met elsewhere. A quantum non-demolition readout is built so the particular variable you monitor can be read again and again with the same answer, whereas a weak measurement trades single-shot certainty for minimal disturbance, relying on ensembles and statistics to build knowledge while leaving the system largely free to evolve. The two ideas often collaborate, a weak coupling to a QND variable, but they solve different problems. Because weak measurements pry so gently, they are ideal for probing foundational questions that strong measurements muddle. For instance, in a double-slit experiment, you can map the average momentum flow across the screen without collapsing the interference pattern by weakly sampling a transverse kick and post-selecting on where the photon lands. The resulting average trajectories are not literal paths a single photon followed, but they summarize how probability current weaves through the apparatus, turning a poetic wave story into a figure you can plot. They also let you test the boundaries of macrorealism and contextuality. By stringing together sequences of weak probes and post-selections, you can check whether a system's properties can be assigned consistent pre-existing values across time, the Leggett-Garg program, or whether the outcome of one question depends irreducibly on which other questions are asked. A hallmark of contextual behavior that weak measurement protocols can expose without the heavy hand of strong projective tests. On the practical side, the method earns its keep in metrology and control. Weak value amplification has measured tiny beam deflections, index changes, and timing shifts with instrumentation that would saturate or drift if you cranked up a direct signal instead. And while it doesn't beat fundamental shot noise limits when all resources are counted honestly, it reshapes technical noise, pushes signals into detector sweet spots, and cancels certain systematics, the kind of win by reframing that matters in real labs. Meanwhile, in quantum information processors, continuous weak readout lets you peek at error syndromes while leaving data qubits mostly undisturbed, enabling feedback that catches dephasing early, tunes gates on the fly, and keeps a fragile computation on track. Combine those streams with quantum smoothing, a Bayesian blend of past and future data, and you can estimate a system's state more accurately than forward-looking data allow alone, and a causal-sounding but perfectly consistent trick that treats the record as a whole rather than as a one-way diary. None of this absolves you from care. Weak measurements are easy to misinterpret if you forget that post-selection rejects most trials and can bias averages, that dark counts and drifts masquerade as anomalous values, and that the choice of meter and coupling determines what weak value you actually read. Good experiments calibrate meticulously, vary the post-selection angle to track how the amplification behaves, flip the signs, a gauge trick, to expose background offsets, and report full distributions rather than only best-case means. The interpretational debates are lively and healthy. Some treat weak values as purely operational tools. Others see them as glimpses of conditional properties defined between preparation and detection, but you don't need a metaphysical stance to use them honestly. As conditional expectations weighted by how the system is filtered at the end, they tell you exactly how a faint nudge to the meter should average out across the selected runs, and that is enough to guide design. If you want a mental model that needs no equations, keep two dials in mind: coupling strength, which sets how much you disturb with each peak, and sample size, which sets how much you can learn by averaging faint signals. Turn the first down until single peaks are kind. Turn the second up until statistics drown the randomness, and align your pre- and post-selections so that the tiny meter kick points most cleanly at the feature you care about. Then, when a result looks impossible, remind yourself it is the average of a filtered conversation, not a single confession. The broader lesson is not confined to physics. Sometimes the only way to learn from a delicate process is to ask lightly, and often to combine answers across time and conditionally on how the story ends, and to accept that the best estimates live in careful averages rather than in dramatic certainties. Weak measurements teach you how to read the almost unmeasurable by shaping what you ask and how you listen, and they whisper a humane method: disturb less, aggregate more, and let inference do the heavy lifting. An approach that, like a hand held near a breeze, can tell you the wind's direction without ever blocking its flow. Rydberg blockade. Preventing excitations by just one atom. Picture walking into a room full of perfectly still atoms and discovering that one decisive whisper can quiet an entire crowd. The moment a single atom is promoted to an enormous, sensitive Rydberg state, its presence shifts the energy of its neighbors so strongly that your laser, which was ready to excite many, suddenly finds the rest off key and falls silent. This is the Rydberg blockade, a remarkably simple idea with surprisingly deep consequences. By exciting one atom, you prevent the same excitation from happening nearby. And that "no, not here" zone, the blockade radius, turns a many-body tangle into a coordinated system that behaves as if the group were a single, larger atom you can address with precision. To see why the effect is so strong, you need only a few facts you can hold in your head. When you boost an atom into a high-principal quantum number, its electron orbits at a huge average distance, making the atom's energy levels exquisitely sensitive to electric fields, including the fields from other excited atoms. Two such giants talk to each other via interactions that can scale steeply with distance, often like 1/6 power when they're off resonance, and more strongly when you tune them into a Förster condition, where dipoles effectively lock, producing a 1/3 fall-off. Take typical values used in the lab, and you find that a single excitation can shift a neighbor's Rydberg line by many megahertz over several micrometers, far larger than the line width of a carefully stabilized laser. So within that radius, only one atom at a time can be raised without detuning the rest beyond reach. The immediate symptom of blockade is a suppression of double excitations, but the more interesting outcome is collective. If you illuminate n atoms all inside one another's blockade spheres, the system doesn't choose which single atom to excite. It shares the possibility across them all, forming a superatom, where the Rabi frequency, the rate at which you can drive the transition, is enhanced by the square root of n, and where the excitation lives as a symmetric superposition that you can create and erase coherently. Prepare two such regions side by side, and you can wire their dynamics together, using the presence or absence of one excitation to condition what happens to the other. The skeleton of a 2-qubit gate in a neutral atom quantum computer. The logic is delightfully concrete. Label one atom, or a small site, as control and a neighbor as target. Apply a pulse that lifts the control's logical one state into a Rydberg level. Then try to flip the target. If the control is excited, the target's Rydberg line is shifted out of tune and the flip fails. But if the control is 0 and stays on the ground manifold, the target accepts the pulse. Finish with a pulse that returns the control from its lofty perch, and you have implemented a controlled phase or controlled knot, depending on the details, purely with light and the built-in courtesy that one Rydberg atom imposes on its neighbors. You can feel the engineering dials in this picture. Choose the principal quantum number to set the interaction strength and thus the blockade radius. Set the spacing of atoms, often arranged in tweezer arrays of hundreds or thousands, to be smaller than the radius for strong gates or larger for independent operations. Pick pulse shapes that minimize leakage to other states and avoid unwanted motion, and compensate residual fields so the giant, sensitive atoms don't wander in energy. Not every blockade is perfect, and that's where the honesty comes in. If the shift is not much larger than the laser's bandwidth, two atoms can be partially excited together, creating errors. If the Rydberg state decays by emitting light, or if blackbody radiation kicks it elsewhere, coherence suffers. If your atoms move because they're warm, Doppler shifts blur the resonance, and if your lasers aren't quiet, phase jitter sneaks in. The craft is to push the interaction up and the noise down so the gate's conditional nature, blocked versus allowed, wins by a wide margin. The same mechanism also organizes space in beautiful ways when you drive many atoms at once, because an excited atom forbids neighbors from joining in. Excitations tend to arrange in patterns with a characteristic spacing, producing density waves and Rydberg crystals, in which the system chooses one from many nearly degenerate arrangements. By detuning the laser and adjusting the drive, you can tune the effective interactions and watch the pattern change from isolated islands to stripes to more complex tilings, not as pictures in a simulation, but as fluorescence maps you can record, atom by atom, with a microscope that resolves individual tweezers. Flip the sign of the detuning, and a cousin of blockade called facilitation appears. Now the presence of one excitation pulls a shell of neighbors into resonance instead of out, so the next excitations prefer to land at a specific distance and, under the right conditions, a single seed can grow an aggregate outward like frost on a window, useful both for exploring non-equilibrium growth and for engineering correlated states on purpose. Blockade's reach into photonics is real, but different from other platforms you might have met. Place atoms under conditions where a weak light field would normally pass due to a transparency trick, and one stored Rydberg excitation can close the window for a second photon, turning the medium into a single photon switch. In free space atomic arrays, blockade sets the ceiling for how many excitations you can hold in a patch, and therefore how sharply you can sculpt collective emission, a path toward directional single photon sources and interfaces to quantum networks. But the flagship use today is in programmable quantum matter and computation. Tweezer arrays can now be rearranged into defect-free registers with arbitrary geometries, lines, honeycombs, fractals, and blockade turns those geometries into spin, models with tunable, long-range links by mapping ground and Rydberg to spin down and up. Sweep the laser parameters and the system can move across phase transitions that textbooks draw, but solids complicate. Or you can freeze dynamics midstream to read out snapshots of how order grows, domain walls move, and correlations spread. Movies that teach you what thermalization means in a clean quantum setting. For computation, blockade gates have climbed steadily in fidelity through better vacuum, quieter lasers, and smarter pulses. Researchers exploit dressing, where you couple ground states weakly to Rydberg levels so that atoms interact without, fully leaving their quiet home, trading a perfect on-off blockade for a soft, tunable repulsion that lasts longer and heats less, ideal for analog simulations or for implementing cost functions in optimization routines. They also play with resonance conditions that amplify interactions at specific distances, making 2-qubit gates faster or many body constraints sharper. None of this is magic. Every improvement pays in practical details. Electrodes near the atoms tame stray charges that otherwise yank giant Rydberg levels around. Cryogenic shields reduce blackbody noise. Better imaging weeds out misloaded sites before a run. Composite pulses cancel systematic errors, and careful benchmarking distinguishes a true blockade-limited error from an alignment slip or a frequency drift. Perhaps the most intriguing part for you to carry is how a negative principle, you may not excite here, becomes a positive design tool. By forbidding simultaneous excitations in a neighborhood, you encode hard constraints directly in physics. So the allowed configurations of the system are the allowed solutions of your abstract problem. The machine doesn't check constraints one by one. It cannot enter states that violate them in the first place, and your job becomes guiding it so that, among the legal configurations, it finds the one that best fits your optimization goal. That perspective also hints at where the frontier lies. Scaling up means finding ways to keep blockades strong and uniform over many sites while reducing crosstalk, and it means mastering new pulse shapes and error correction strategies that can rescue information when an atom blinks out or a chain breaks. Exploring new physics means using blockade not just to keep excitations apart, but to choreograph when and where they do meet, via facilitation shells, spatially patterned detunings, or time-dependent drives, to build textures of quantum matter that have no easy analog in equilibrium solids. If you're looking for a clear mental model with no equations, imagine a neighborhood of porch lights wired so that when one turns on, it slightly raises the voltage threshold for the houses within. A few doors, a single switch flips, and for the moment, the neighbors cannot glow, but the next block over still can. If you drive the street with a periodic wave that tempts all switches, clusters light up with a preferred spacing. And if you program the wave to respond to what's already lit, you can draw patterns that obey your rules without ever checking them line by line. The physics enforces them for you. That is the quiet strength of the Rydberg blockade. One atom's decision becomes a zone of influence, local constraints become global order, and hardware that could have been noisy and independent learns to act with a coordinated, collective discretion. As you move from curiosity to application, the message remains the same. Shape the interactions so that one choice naturally excludes the wrong neighbors, and you will find that even in a crowded quantum room, a single voice can organize the rest. Topological photonics. Light that won't get lost. Picture trying to send a whisper through a crowded maze. Every corner snags the sound, every crack steals a syllable. Then imagine redesigning the maze so that along its outer wall, there, forms a narrow promenade where the whisper glides cleanly, skirting sharp bends and shrugging off rough bricks. That is the promise of topological photonics. Not a new kind of light, but a new way of arranging materials and timing so that optical waves acquire roots that are robust by design, guided less by fragile details and more by global patterns you stitch into the structure itself. The starting point is simple enough to say. When light propagates in a periodic medium, think of a crystal of holes in a dielectric or an array of coupled resonators. Its allowed colors and directions form bands separated by gaps, and by nudging symmetry in the right way, you can end up with bands that carry a hidden twist in how the waves wind through their momentum space, a twist you cannot iron out without tearing the pattern open, and this twist obliges the crystal to host special boundary channels where the gap closes smoothly and light finds a protected path. You do not need equations to feel the heart of it. What matters is that the protection comes from the overall organization, not from micrometer-perfect walls. So a seam of light along the edge keeps its character even as you add dents or drive it around tight corners. How do you give photons this kind of obligation? One route uses magneto-optical materials that break the symmetry between forward and backward propagation. Ferrets like yttrium iron garnet under a steady magnetic field at microwave or infrared frequencies, so that the interior bands carry a handedness and the boundary supports a single marching direction with no backwards partner to scatter into. Another route, friendlier to silicon chips where strong magnetism is awkward, creates a synthetic magnetic field by modulating couplings in time, phase shifters, or helical waveguide paths that make light feel as if it had looped through a region with a flux, even though no real magnet threads the device. And this time-patterned Floquet trick opens gaps with topological character in which edge modes cruise past imperfections. A third strategy leans on crystal geometry rather than broken time symmetry. If you build two photonic crystals that are mirror images with slightly different internal phases and then join them, the interface can host guided modes tied to a valley or pseudo-spin degree of freedom, so light with one internal label travels one way and the other label travels the other, and ordinary roughness that respects the protecting symmetry cannot easily flip the label, which is why the path resists. Backscatter. Designers mix and match these ingredients. Magneto-optic bias, where it's practical, dynamic modulation where it's not, geometric phase where symmetry allows, to craft lattices of rings, rods, or holes that behave like tiny cities of guided light with one-way streets along the rim. The lab signatures are satisfying and visible. In microwave plates drilled with hexagonal patterns, a pencil-thin beam launched at the border loops around a square obstacle without noticeable reflection. On silicon photonic chips, chains of microring, resonators arranged into topological lattices route a telecom band signal around sharp hairpin turns with losses that are remarkably insensitive to small fabrication defects. In femtosecond written glass waveguides, helical trajectories imprint a time-periodic coupling that creates an optical analog of a topological insulator, and a spot of light injected at the edge surfs the perimeter in one direction, ignoring missing links like a hiker who never leaves the cliff path even when steps are broken. Push beyond edges and you find higher-order designs where the protected modes hide not on the border, but at corners. Tiny cavities that trap light strongly at the meeting of two interfaces because the lattice carries a more intricate kind of topology. Those corner states serve as robust, ultra-compact resonators for sensing or for feeding lasers that prefer a single, stable tone. Practical consequences spill out quickly. Engineers can build delay lines and beam splitters whose performance stays steady across process variations, a welcome property when you need to assemble thousands of elements on a wafer. Isolators and circulators that protect lasers from back reflections usually rely on bulky magnets, but topological schemes offer magnetic-free alternatives using modulation that mimic one-way traffic in a footprint small enough for a chip. And perhaps most eye-catching, topological lasers put the gain medium on a protected boundary so that only one extended edge mode survives competition, leading to single-mode emission that resists the usual quirks of disorder. If one ridge has a slight nick or one resonator's frequency drifts, the global edge path simply routes around it and the lacing mode stays coherent. Because loss and gain change the rules for waves that can grow or die, the field has embraced non-Hermitian physics too, using carefully patterned absorption to steer energy into the desired channel and exploring exotic features like exceptional points without letting fragility ruin the function. The same robustness is attractive in quantum experiments. A chip that guides single photons from entangled sources into a small interferometer benefits from border paths that do not scramble phase when a lithography stitch is imperfect, so two-photon interference remains high. Quantum walks of single photons on a topological lattice spread along predictable fronts, even with small missing sites, turning fragile state preparation steps into practical modules. And corner states can host bright, stable emitters coupled efficiently to a single output, a route to uniform photon sources, where previously each nanocavity needed hand-tuning. None of this means topological photonics is a magic cloak. Protection is conditional, not universal. A design that relies on a bandgap will falter if defects are large enough to close that gap locally. A channel secured by a symmetry can still be upset by features that violate that symmetry. For instance, magneto-optic bias must be maintained, or a Valley Hall interface must preserve the mirror constraint. And ordinary materials still absorb and heat, so one-way travel does not cancel loss. It simply prevents reflection. Moreover, creating synthetic fields by modulation adds drive tones that can introduce noise, and magneto-optical solutions at true optical frequencies remain materials limited, which is why many demonstrations start at microwaves and migrate upward as fabrication and materials improve. Yet even with those edges in view, the engineering payoffs are real and growing. Robust interconnects in photonic neural accelerators that shuttle light between matrix multiply cores without crosstalk spikes. LiDAR chips whose steering gratings are fed by border waveguides that keep phase stable across thermal gradients. Biosensing rings that couple to corner modes, so a tiny change in refractive index shifts a sharp, protected resonance rather than a mush of competing peaks, and integrated frequency combs that dump unwanted back-propagating power harmlessly into non-coupled channels instead of destabilizing the pump. The approach also favors modularity. Because protection is global, you can snap topological sections together with less fear that a small mismatch ruins performance. So future photonic PCBs may route light the way printed circuit boards route electrons today, but with border lanes that hold phase and amplitude steady even when the board flexes or ages. Underneath the hardware sits a conceptual shift that is worth holding on to. Instead of polishing every surface and measuring every bend to death, you design a pattern whose whole enforces the behavior you want and whose exceptions are expensive for the waves to access. And then you keep the few conditions that matter: gap open, symmetry respected, while letting small mess ride. That attitude doesn't replace craftsmanship. It redirects it toward what actually matters, freeing you from the anxious detail, chasing that so often blocks scale. If you want a mental model that needs no symbols, picture a ring of rooms with doors between them. By decorating the doors with simple rules, this one only opens clockwise, that pair swings together. You create a corridor around the outside that a runner can circle reliably, even if a few doorways are scuffed or tight. Inside the ring, rooms are quiet because the rules create a band gap of sorts, and only along the decorated boundary do you get motion. Now imagine you can program those door rules electrically in real time, and even reshape the ring into a maze. You've arrived at reconfigurable topological photonics, where phase shifters and modulators redraw the map, so a network learns new routes without swapping hardware. The human echo is gentle but pointed. When you need reliability in a messy world, sometimes the better move is not to fight every defect, but to choose an architecture that forgives them, to embed your path in a pattern that prefers success. Light that won't get lost is not a boast that ignores physics. It is a careful use of physics to make guidance the default. And as these ideas settle from demonstrations into devices, the promise is clear. A generation of optical systems that keep their bearings even when the maze is imperfect, that carry signals, images, and qubits along borders that refuse to backtrack, and that remind you, in the language of waves, that robustness can be designed on purpose rather than hoped for by accident. Ultra-fast spectroscopy, watching atoms move in femtoseconds. Start with a clock you can't see and a heartbeat you can't feel. A millionth of a billionth of a second, the span in which a bond quivers, an electron leaps, or a crystal breathes, ever so slightly. And imagine that you want to watch those motions as clearly as you watch a bird take off from a branch. Ultra-fast spectroscopy is the art of building that impossible camera, not by filming continuously, but by arranging two flashes of light, a pump to start a specific motion and a probe to ask what changed, then repeating the event, while sliding the delay between them until a flipbook of femtosecond snapshots turns into a movie of matter learning to be something else. The reason this works is simple to state and rich to execute. If your flashes are shorter than the motion you care about, and if you can control their separation with exquisite regularity, then every repeat of the experiment freezes the system at a slightly different moment, and the signal you collect, how much light is absorbed, what color it emits, which electrons are ejected, or how an X-ray diffracts, becomes a function of time that you can stitch into a narrative of twisting. Nuclei and migrating charge. Pump and probe can be any flavors you need. Visible pulses to trigger a dye, mid-infrared bursts to watch a specific bond vibrate, terahertz pings to sense the rise of conductivity, ultraviolet to kick out photoelectrons, even femtosecond X-rays, from a free electron laser to record the shifting positions of atoms directly. And the choice lets you decide whether you want to follow energy, structure, or both. Under the hood are two enabling tricks that feel like magic but are engineering. First, lasers that deliver pulses so brief they carry the world's most impatient brightness, made possible by stretching and recompressing light, so you can amplify gently without breaking glass, then squeezing it back into a packet only a few cycles long. Second, timing control finer than a human can picture, accomplished by splitting paths on a table and nudging mirrors by hair widths, so the probe arrives tens, hundreds, or thousands of femtoseconds after the pump. Again and again, stable enough that when you average over millions of repeats, the noise of the lab cancels and the tiny changes of the sample remain. With those two in place, the technique becomes a language for seeing what textbooks describe only in after-the-fact terms. Transition states that used to be dots on a diagram now register as brief plateaus in a signal before products appear. Conical intersections, the fast, hidden detours where a molecule sheds electronic energy by sending its nuclei through a crossing of states, announce themselves as sudden losses of fluorescence and shifts in photoelectron spectra that happen in just a handful of femtoseconds. In solution, you can watch the solvent itself respond, a delayed rearrangement of the liquid cage that tells you how the environment either cushions or catalyzes change. In solids, a jolt to a semiconductor lets you track hot carriers as they cool into the band edges, then trap or recombine. Information that explains why some solar absorbers turn light into current efficiently, while others waste it as heat. Knock a crystal lattice with a sub-picosecond burst and a coherent phonon, a collective vibration, rings like a bell you can hear in the reflected light, revealing stiffness, symmetry, and how structural waves launch phase transitions. And if you build the experiment with more colors and more timing axes, two-dimensional spectroscopy, you can watch energy migrate through networks of coupled vibrations, or chromophores, separating cause from coincidence by drawing maps where peaks shift and split as couplings strengthen or fade. The field hasn't stopped at femtoseconds either. By generating high harmonics, new colors born from driving electrons so hard they emit flashes when they snap back, you carve attosecond bursts that let you follow purely electronic motion. Before the nuclei even twitch, timing how an electron escapes, how screening builds, or how a core hole pulls neighbors in brief measurable steps. Pair those bursts with synchronized infrared fields, and you can streak photoelectrons to read subcycle delays, turning what once was instantaneous ionization into a sequence you can actually clock. If this all sounds like wizardry, there's honest housekeeping underneath. Your time resolution is limited by the pulse duration and by how precisely you know when the pulses meet. So you characterize them relentlessly with techniques that unfold their shape in time. The very intensity that makes pulses brief can cook fragile samples, so you translate the target, dilute the beam, or refresh the surface so each shot sees something new. Signals are small, so chopping beams, referencing against a clone path, and locking delays guard you against drift masquerading as dynamics. And in liquids or biomolecules, you accept that thermal motion blurs details, then design your observable, vibrational tags, isotope edits, site-specific labels, so the blur itself teaches you which motions matter. The payoffs are tangible. Ultra-fast snapshots establish that the switch in your eye's retinal pigment happens on the scale of tens to hundreds of femtoseconds, fast enough to outrun unhelpful side reactions. They revealed that certain DNA bases dump harmful energy through rapid protective crossings, a built-in sunscreen that chemistry alone couldn't have proved. They showed how catalytic metals breathe during reactions, opening and closing adsorption, sites in sync with electron flow. They mapped how perovskites and other emerging semiconductors shepherd charge away from defects, explaining why simple processing sometimes yields startlingly good devices. They let materials scientists melt magnetism or charge order with light and watch how order reforms, teaching us which interactions underwrite a phase. And in biology, optical tweezer experiments often read tiny forces, but it's the ultra-fast methods that catch the first femtosecond steps when a protein's chromophore jumps, setting the stage for the slower structural dance you see later, under a microscope. None of this means the method is a universal microscope that sees whatever you dream up. You still choose your questions carefully, because every probe couples to some motions and ignores others. You still deal with competing pathways that overlap in time, which is why multidimensional methods and complementary probes matter, and you still need theory as a partner to turn spectra into structures and intensity traces into coordinates. Because the raw signal is a projection of a complex movie, and honest interpretation requires models that you challenge from several sides. Yet the deeper reward is conceptual. Before ultra-fast tools, chemistry and condensed matter physics were dominated by equilibrium pictures, start, end, maybe a dotted line through a mountain pass, and the times in between were fables. Now you can see that many outcomes are decided early by fast funnels and couplings, that some barriers are bypassed by clever collective motion, and that designing function means designing the first instance as much as the final state. Carry one mental image with you. You are not turning on a magical slow-motion camera. You are starting the same event thousands of times and asking the system, gently but insistently, where are you now, at different delays, then assembling its answers into a coherent arc. And carry one practical echo too. When a process seems too quick to grasp, sometimes the way forward is to divide time into controlled instants, to repeat patiently, to align your questions so the faint signal adds and the noise cancels, and to let the story emerge from carefully timed glimpses, rather than from one overwhelming stare. That is what it means to watch atoms move in femtoseconds, a craft of timing and tenderness that transforms the blur between cause and effect into frames you can study, learn from, and ultimately use to shape new reactions, new materials, and new ways of catching the world in the act of becoming itself. Nano-Mechanics. Measuring forces, smaller than a whisper. Imagine resting your fingertip on the quietest table and trying to feel the tug from a single molecule as it folds. The brush of two surfaces separated by the thickness of a few atoms, or the faint pressure that light itself exerts when it ricochets. Impossible for you, but not for nanomechanics, the craft of shrinking springs, drums and strings until their slightest motion becomes a readable sentence about forces smaller than a whisper. The basic move is disarmingly simple. Carve a mechanical element, an ultra-thin cantilever, a tensioned nanostring, a graphene drum, a silicon carbide beam, so small and light that even a picometer of deflection represents a measurable fraction of its size. Then watch that deflection with a readout that converts motion into something you can store and compare, whether it's the phase of a reflected laser, the charge on a capacitor, the resistance of a piezoresistive bridge, or the frequency of a microwave cavity it is coupled to. You treat the device like a guitar string. You can neither see nor touch directly, and you listen with interferometers, optical cavities, or sensitive electronics, while the world nudges the string with forces that used to be invisible. Van. De Waals attraction as a tip glides near a surface. Magnetic pulls from a handful of spins in a gradient. The tiny extra drag when a single virus adheres. The sudden ease when a protein unfolds. Or the pressure between plates that Casimir predicted would appear from nothing more than the shape of the vacuum between them. Once you're listening this closely, you meet the first honest limit. The world will not stop wiggling for you. The thermal agitation of atoms shakes every resonator randomly, setting a floor under your sensitivity that depends on its mass, its stiffness, and how quickly it leaks energy to the environment. So the craft flows in two directions at once, toward high-Q designs that ring like bells for a long time after a flick, and toward quiet environments that keep the flicks rare and gentle. Vacuum to remove viscous drag, low temperatures to calm, thermal noise, surface treatments to quiet friction at the atomic contacts, even feedback that senses motion in real time and applies a counterkick to narrow the jitter. You also take advantage of resonance the way a playground swing does, not to amplify a signal indefinitely, but to make your device most responsive at a particular tone, then drive or monitor at that tone and use lock-in detection to pull a buried response out of a sea of broadband noise. With that foundation, the techniques branch into two families that you can hold in mind. In static mode, you push and read the deflection directly, ideal for measuring adhesion, contact mechanics, and the stick-slip transitions that happen as a tip slides across a lattice. In dynamic mode, you let the resonator sing and watch the frequency and line width change, because a tiny added force or mass shifts the pitch and the damping by an amount you can calibrate. This is how nanostrings weigh adsorbed molecules 1 billion, times lighter than a grain of dust, and how torque magnetometry reads the magnetization of atom-thin crystals by the way they twist a suspended beam in a known field. Atomic force microscopy, the workhorse of the field, uses both habits in liquid and in air. It maps forces across a surface one line at a time, feels the stiffness of a cell's cortex without tearing it, and tracks binding events between a functionalized tip and a target receptor by the little pops in force as bonds form and rupture. Cousins reach beyond biology. Magnetic resonance force microscopy detects the tugs from single electron spins, bringing magnetic imaging to a scale where conventional sensors cannot go, and microtorsion balances test gravity's shape at sub-millimeter distances by looking for deviations in the feeblest twists. As you push lower in force, another limit appears that is philosophical as much as technical. Measuring introduces its own disturbances. The same photons that let an interferometer see an angstrom of motion also kick the mirror with radiation, pressure shot noise, and the electrons that read a piezoresistive bridge jostle as they flow, adding little random forces. There is even a standard quantum limit that draws a boundary between how precisely you can know position and how gently you can leave the momentum alone. And modern sensors now live close enough to that boundary that design choices about which slice of the motion to monitor and when have measurable consequences. Clever workarounds exist. Reading one quadrature of an oscillation so back action lands in the other, shaping the light's fluctuation so they squeeze where it hurts least, or using dissipation-free coupling elements to keep the probe from becoming a break. But the deeper point is that the meter and the measured are a duet, and honesty in calibration requires accounting for both voices. Calibration itself is a quiet art. You can tether your scale to thermal motion. If you know the temperature and watch the random jitter long enough, you can deduce the spring's stiffness without applying any external force. You can press on a known hydrodynamic drag by sweeping fluid past the cantilever and letting viscous laws set the reference. You can deposit or remove a known mass and watch the pitch shift, and you can cross-check with material standards so your attonewton means the same this week as it did last month. These routines matter because the field runs on tiny differences that would vanish into systematics if you were careless. With trustworthy sensors, the menu of experiments is startlingly broad. Measure the time it takes an enzyme to cycle by holding a substrate at the end of a soft linker and feeling each catalytic stroke. Watch a battery electrode swell and shrink by the width of a few atomic layers as ions insert and leave, tying mechanical strain to electrochemical health. Probe the viscoelastic landscape inside a living cell by jiggling a trapped bead and feeling how the local cytoplasm resists at different frequencies. Map capillary forces as humidity creeps up, explaining why micromachines seize in damp air. Weigh airborne nanoparticles in a cavity by the shift in an acoustic or optical mode as each speck lodges. And, at the frontier, suspend a neutral nanosphere in vacuum and cool its center of mass motion until it becomes a force meter that can see zeptonewton, nudges from patch charges, or faint gas winds. A step toward using mechanics to test fundamental noise sources in the vacuum itself. None of this is a promise that nanomechanics erases difficulty. Surfaces foul and change with time. Adsorbates add their own wiggly personalities. And in liquids, the same thermal agitation that makes life possible also washes faint signals constantly. But the response has been to design around reality rather than to wish it away. Coatings that resist adsorption, geometries that push strain into crystalline directions with fewer defects, multiplexed arrays that measure many spots at once so outliers reveal themselves, an analysis that turns the spectrum of noise into a fingerprint of what, exactly, is limiting you today. The human echo in all this is easy to miss and worth keeping. Learning to sense the almost unmeasurable is less about force and more about agreement between a resonator and its readout, between your question and the tone where the answer is loudest, between your patience and the statistics that lift a signal above noise. You do not conquer the small by smashing it with brighter beams or heavier probes. You coax it by choosing the right mass, the right stiffness, the right bath, and by listening in a way that adds rather than overwhelms. And when you assemble those choices, a light string in vacuum, a stable laser ear, a calibration tied to motion nobody caused, you find you can feel the weight of a single layer of atoms settling, the pull of a surface no hand could touch, the tiny kick of a reaction as it lets go, and you carry away not just a number, but a way of paying attention that scales beyond the lab. Set the sensitivity where it belongs. Honor the noise that cannot be banished, and let your measurements be small enough to matter. Spintronics, computing with the twist of electrons. What if the bits your computer flips weren't carried only by moving charge through hot, resistive metal, but also by steering a built-in compass each electron already owns? The tiny spin that points roughly up or down. And what if learning to route and twist those compasses let you store data that stays put with the power off, switch states with nanosecond nudges, and push information without the waste of shoving billions of charges around? That is the promise of spintronics, a field that treats spin as a first-class signal alongside charge. And you can grasp the core idea with a few grounded facts. An electron's spin behaves like a microscopic magnet. In ferromagnets, many of these tiny magnets align, creating preferred directions. And electrons whose spins match or oppose that alignment meet different resistances as they pass through layered materials. So by stacking ultra-thin films and controlling their relative orientations, you can turn electrical resistance into a readable, writable bit. The earliest dramatic proof was giant magnetoresistance, GMR, where two ferromagnetic layers separated by a non-magnetic spacer conduct easily when their magnetizations point the same way and poorly when they are opposite. The effect that made hard drive read heads suddenly far more sensitive and shrank your music library into your pocket. A cousin, tunneling magnetoresistance, TMR, swaps the metallic spacer for an atomically thin insulator such as magnesium oxide. And because quantum tunneling depends on how spin-polarized states on each side line up, the resistance contrast becomes even larger, yielding rugged sensors and the heart of magnetic random access memory, MRAM, cells. The clever twist is how you write those cells. Instead of using an external magnetic field, modern devices use the current itself to deliver angular momentum, spin transfer torque, STT. So a pulse of spin-polarized electrons pushes the free layer's magnetization to flip, giving a fast, non-volatile bit with endurance measured in trillions of cycles and switching times in the single-digit nanoseconds. Push the physics further with heavy metals like platinum or tungsten next to a ferromagnet, and the spin Hall effect appears. An ordinary charge current in the heavy layer creates a sideways flow of spins that spills into the magnet and exerts a spin-orbit torque, SOT, letting you switch magnets with separate write and read paths that scale well in dense logic. Because spins can propagate as collective waves, magnons, rather than as drifting charges, researchers also explore magnonics, where information rides on low-loss precession in magnetic films, potentially reducing heating dramatically. Compared with pushing DC current, and because spin can be generated by heat gradients as well as by currents, spin caloritronics uses effects like the spin-Seebeck effect to turn waste heat into spin signals that a detector can read electrically. At the device scale, the menu is expanding. SOT MRAM is moving from prototypes into caches where speed and endurance matter. Domain wall logic and racetrack memory aim to shift walls between up and down regions along nanowires with short pulses, packing multiple bits per track, and swirling textures called skyrmions, tiny, topologically protected spin whirls, can be nucleated, moved with remarkably low currents, and read out, suggesting future memories, where each skyrmion is a data token that resists defects better than a crude domain. There is also a quiet revolution in materials that carry spin well. Half metals and Heisler alloys promise nearly 100% spin polarization for strong signals. Graphene and other two-dimensional materials let spins travel long distances with little scattering, acting as highways that don't scramble orientation. Transition metal dichalcogenides and engineered interfaces add tunable spin-orbit coupling so that gate voltages can steer spins electrically. And topological insulators provide surface channels where spin is locked to motion, enabling efficient spin injection and detection without large magnetic fields. Meanwhile, antiferromagnetic spintronics flips a common assumption, using materials whose internal moments cancel so there's no stray field at all, and wins speed. Their natural resonances lie in the terahertz range, so switching can be orders of magnitude faster than ferromagnets. And because they don't broadcast magnetism, neighboring devices can sit closer with less crosstalk, an attractive trait for dense memories and hidden magnetic tags. None of this is hype without edges. Writing spins still costs energy, and too large currents heat the stack. Interfaces must be atomically tidy, or spin polarization decays before it does useful work. Variability across billions of cells can smear switching thresholds, and integrating magnetic stacks with standard CMOS requires careful material choices and low-temperature steps late in fabrication, all of which industry tackles with better barriers, smoother crystalline growth, and verification at the level of wafers, not just single devices. Still, the wins are real and already in products. Embedded MRAM that replaces slower, power-hungry flash in microcontrollers, robust sensors in cars and phones that read position and angle from tiny changes, in resistance without wearing out, and prototype logic blocks that demonstrate non-volatile computing, where turning power off erases idle leakage rather than your state. Look a step ahead and you see paths toward neuromorphic elements that are naturally noisy and hysteretic in just the ways some learning algorithms prefer, probabilistic bits where the likelihood of a 1 is tuned by current and temperature for stochastic computing, and cryogenic-friendly spin devices that play well with superconducting circuits in sensor front ends. Perhaps most important, spintronics changes the framing of compute per joule. By storing state magnetically, you avoid refreshing capacitors as DRAM does. By moving spins instead of charges, you can trade resistive heating for wave propagation. And by separating red and right paths, you can tailor energy use to what the workload actually needs, instead of paying the worst-case price for every operation. The science behind the scenes remains honest and concrete. Spin is an intrinsic, quantized property. Spin-orbit coupling converts between spin and momentum. Interfacial symmetry decides whether a given stack will encourage or hinder that conversion. And device engineers pull those levers with thicknesses measured in atoms and pulses measured in picoseconds to meet real constraints like retention at 125 degrees C, bit error rates that don't wreck caches, and write energies that fit within mobile budgets. If you want the cleanest mental model with no algebra, imagine each bit as a tiny weather vane and each electron as a breeze carrying not only push, charge, but also twist, spin. Arrange vanes in stacks so that twist helps or hinders the path of the breeze, and you've built a sensor or a memory. Add channels where breeze becomes twist and back again, and you've built interconnects and logic. Then engineer the neighborhood so the vanes flip only when asked and keep their direction when the storm passes, and you've earned non-volatility. The human echo, as always, is about strategy. When shoving harder makes you hot and slow, look for a different handle on the same system. By choosing to compute with the twist rather than the shove, spintronics shows a route to devices that remember without power, switch fast without fury, and turn materials' quiet internal order into work. You can count, a reminder that progress often comes not from adding more of the same, but from noticing the second lever your system quietly offers and designing around it with care.